Hello, you guys ready? All right, let's do it. So got some good information for you here today. I'm Harry Weinman. I'm a forecaster at the Storm Prediction Center. Here with Cameron Nixon, who is a research scientist with us now. And we actually just put all this together. You're the first to see what's going to be the newest information for the Weather Service RAC course. So you guys will be our trial people here. So bear with us. It's a lot of information. I'm going to just do a quick poll of the audience here to start. Raise your hand if you have never seen or messed with a Hodograph before. Okay. And then everyone else is kind of comfortable-ish, something. Cool. Well, we're going to kind of go through the beginning stuff quick because there's a lot to get to. So let's just start off to motivate this. So on the left, obviously, we have the SPC. This is mainly used to assess thermodynamic aspects of the environment. And on the right is the Hodograph. And the Hodograph is essentially just a plot that is generated from the wind barbs on the left. But what we'll find is that the Hodograph is going to be a much better tool to assess the details of the vertical wind profile and therefore the shear. And that matters in forecasting organized severe storms. So what is the Hodograph? It's a plot of vertical wind shear, which is just the change in wind speed or direction with height. It's very useful for identifying a lot of different aspects of the kinematic environment that really influence the organization of storms, such as wind shear, storm relative winds, horizontal vorticity. We'll talk about Streamwise, Crosswise, SRH, just tons of different stuff you can get from this. In general, the length and shape of the Hodograph have an influence on how convection is going to behave, for a lack of better terms. So let's just see how a Hodograph is plotted to start. So we're going to use a polar coordinate system for this. Most people should be familiar with that from their classes so far. The way this plot works is from the origin, wind speed increases radially outward. So each ring, as you get further away from the origin, is stronger speed. The origin represents 0 knots, so that's essentially a calm wind. 0 knots, 0 direction. Axes are going to represent directions, essentially. So in this case, we're in UV space. You can do lots of different things with this, but the point is here, we're going to plot wind vectors on this and then eventually draw a Hodograph. So given a southeast wind, we're going to take a vector starting at the origin and point toward the northwest. That's the wind is blowing toward the northwest or from the southeast. And you notice that the wind vector stops at 20 knot, that range ring. That is the speed of the wind. So for the Hodograph, we're going to do this for the whole profile. So here on the left, take all the wind barbs, convert them to vectors, plot the vectors on the polar coordinate system. Simple as that. Each vector is labeled with the corresponding altitude that that wind is blowing at. So next, if we connect any two of these wind vectors, that's actually a vertical shear vector. The reason for this is because we're simply taking a bulk wind difference between two different levels. That is vertical wind shear. So the longer these shear vectors, no surprise, the stronger the shear is in that layer. So in this case, you can see we have stronger surface to 1 shear than 1 to 2. If we do this for every point on the Hodograph, this traces out the Hodograph. So the Hodograph is just shear vectors with height, just like we said in the beginning. So in practice, we don't plot the vectors, just the curve connecting the tips of the vectors, which is the Hodograph. Hodographs are color-coded by level. This makes assessing strength of shear at any given layer much easier. So just quickly glancing at this, it's very clear that the surface to 1 shear is strong. Also 1 to 3, if you were to use that layer, is very strong. So this would be an interactive part for the modules for the RAC course. We basically just ask people, click on the Hodograph to draw the vector. So in this case, you would draw in that bottom left quadrant at the 10 knot. Then you'd click the next point would be to the west at 20, and then from the south at 20. So you kind of get the idea. So we're just plotting the tips of each vector and connecting them with shear vectors. So I'll pose the question for everybody. Where's the shear the strongest in this Hodograph? Yep. You got it. Longest vector there. So pretty straightforward. Where can you find hodographs? A lot of different sources you can see here. Of course, observed soundings, also forecast soundings. So this is from the SPC sounding site. We also have VWP, that's VAD wind profiles generated from radar data that's sampling precip. These can generate hodographs. We use these really often in SPC operations, especially during the mesoscale to watch phase. We have plan view plots. So this is the hodograph map that Cameron had a lot to help with on the SPC mesoanalysis page under wind shear. Take a look at that one. That's another one we use quite a bit in ops. And ACARS data, so planes collecting upper air. So anything that collects upper air wind data, you can get hodographs. And then, of course, lots of different model sources. So summarize, hodographs are plotted the vertical shear with height. The length and the shape of the hodograph affect storms. Pretty straightforward. And we now have a hodograph plotted now. Does anyone have any questions? We're all good. We can plot a hodograph. You guys back there that have never seen one, is that helpful? Say it again.
I didn't know what that was using or not. That's why I was like, how do you figure that out?
Yep, it's just anywhere where you have wind sampled with height, you can plot a hodograph. So that's just often the cases from these soundings. But is that helpful for you guys? Cool. All right, let's move on to Cameron here for bulk shear. These are just going to build on each other. So we start from basically nothing and build up to being experts.
Yep. So each lesson should get harder and harder and harder, and then you'll just suddenly like wake up and now we're on expert level stuff. So don't want to miss when that transition happens. This is going to be on bulk shear and how to find this on a hodograph. So what we mean by bulk shear is a difference in wind between any two levels. So if you can, see this right here, we're drawing this from the surface to 6 kilometers. That's our 0 to 6 kilometer bulk shear. So in this case, right, we can take our surface to 6 point, and you can kind of count how many range rings we are in a row. We got about 6, so it's about 60 knots of bulk shear. So, now you can kind of envision where a 0 to 3 kilometer bulk shear vector might be. And then we can draw that like so. And so what kind of gets lost in translation is how much of the hodograph actually matters for convective storms. So, sometimes we have, say, a shallow storm depth, right? And our equilibrium level here, which is really as tall as your storm is going to get in this environment. This is where we're using a skew T. This is kind of as tall as your storm could get. So we're only going to be feeling these winds in the lowest, say, 8 kilometers or so. We can kind of neglect all this wind above because we're above the thunderstorm. It's not really feeling that. So then in this case, right, what we could do is take this hodograph and kind of just omit everything above 8 kilometers. And that's kind of how we would mentally do this math. But we also have the effective inflow base to worry about. And this is where, say, air might be too stable for a storm to lift up into its updraft. So in this case, when we have a stable layer and we have this little thingy telling us that the inflow base is around 850 meters, we can kind of neglect the winds below that level. And those winds are actually substantial oftentimes, right? You see this really big curve here in the lowest levels. We're actually going to get rid of most of that. And that's kind of what we're left with. Because, right, in these environments where you're literally elevated above a stable layer, especially when your stable layer is strong, we're probably not going to be worrying about that shear very much. So what effective bulk shear does, if you've ever seen this on, say, a plan view like the SPC mesoanalysis, this takes into account both of these things that I just talked about. So both our equilibrium level and our effective inflow layer base. So this makes it really easy for you to say, okay, hey, what is our bulk shear today? I don't want to even look at the skew T. What is our bulk shear? And this is going to give you a pretty good kind of first guess. And it's going to be useful in a wide variety of scenarios. So we could do this one here. Which hodograph has stronger 0 to 6 kilometer shear? The one on the right. Yeah, that's right. Which is stronger 0 to 1 kilometer shear? Left. See, so using just one of these shear vectors in a vacuum is not going to tell you a whole lot. That's why looking at the Hodograph shape and plan views of Hodograph maps are my favorite. And so why we're talking about bulk shear is that stronger bulk shear can create stronger convective storms, larger convective storms, more organized storms, and longer lived storms. Here's my little doodle here. Usually when we have weak shear, we're dealing with more single cellular convection, but stronger shear can lead to more hazardous storms like this case here. So usually when we're, say, above 30, 35 knots or so, you usually have a risk of supercell storms, and we'll talk a lot about those later, both discrete and in convective lines. And when you have less than 25 knots or so, you're usually dealing with a more messy single cell, multi-cell, shorter lived convective storms. So for a summary, convective bulk shear is the difference between two levels on a Hodograph. Shear matters to storms, especially in between the effective inflow layer base and the equilibrium level height. So we're not always going to use that whole Hodograph. We're going to use kind of a subset of that Hodograph. Effective bulk shear is a really good go-to because it takes both of those into account. And then stronger shear could support more hazardous storms. So now we're going to bring it to Harry again. I love this.
All right, so now we're going to talk about Hodograph shapes. We talked a bit about Hodograph length with the bulk shear, and now we're going to talk about the different shapes. So shape of the Hodograph can help us determine basically how storms are going to evolve, or like I used that word, behave. It's basically just how these things are going to change with time. And the shapes can really help with this. So in this section, we're not going to tell you necessarily why these shapes correspond to different behaviors, more so just get the pattern recognition in your head. You see a shape, you kind of think a certain evolution. Later on, we're going to talk about the reasoning why. So here we have a unidirectional wind profile. These create straight Hodographs. When we say unidirectional wind profile, that's the direction of the wind with height is not changing. It's unidirectional. This often gives us these straight Hodographs that support mirror image cell splitting. So everyone is, any severe storm weenies out there know, you've seen this left and right splits. This is very common with the straight Hodograph. The left and right movers tend to split away from the shear vector. So in this case, if you were to draw the shear vector on this Hodograph, it would essentially be the Hodograph since it's straight. So you can see storms splitting apart from the Hodograph. This is another example of a straight Hodograph, but it's actually a veering wind profile. And the reason we show this is to get at the idea that, that the shape of the Hodograph is related to the vertical wind profile, but just because it's veering doesn't mean you're getting at a curved Hodograph. You can get different shapes with different ground relative winds. So always got to look at the shape that corresponds to the wind profile. In this case, similarly, it's still straight Hodograph, so we're going to expect left and right moving storms, the potential for lots of cell interactions, left movers kind of banging into right movers at times. And what you'll note here is that this Hodograph is oriented zonally. The other one was more of a southwest northeast. Storms are going to behave similarly because it's the shape of the Hodograph that influences all this stuff, not necessarily the orientation of the Hodograph itself, with all else being equal, which is typically not the case, but just focusing on shapes here. Here's a curved Hodograph. This is, we call clockwise curved. It's the curvature, how the curvature changes with height. So in this case, you can see it turns clockwise with height. These are found oftentimes in warm air advection regimes. As we know, veering is associated with a thermal wind argument with warm air advection. So this can support splitting storms also, but you're going to see more dominant right movers with this low-level Hodograph curvature. And this can actually reduce the potential for cell interactions compared to the straight Hodograph. Here's another veering wind profile, except more strongly veering, which leads to more Hodograph curvature. So in these are going to be found in stronger warm advection regimes. Sometimes you'll see these kind of shapes in tropical type systems, warm core deals. And these ones are going to even more so favor the right mover. So basically the idea here is the more clockwise curvature, the more the right mover is going to be favored. In this case, actually, we rarely see the left mover. It's oftentimes completely suppressed with this shape. We'll show why later. This is a backing wind profile, cold advection through the thermal wind. Counterclockwise curved hodograph comes out of this. And this would, in theory, support dominant left movers and splitting storms, but in the northern hemisphere, since this is associated with synoptic scale descent, a backing wind profile, it's going to be less common than the other version. Here's a fun one. This is the veer back. It's an N-shape, whatever sort of kind of hodograph. These can be found kind of in the wakes of troughs. Cold fronts aloft are another one, and then in cold core systems. So basically, you see this alternating shape through the profile. It goes from clockwise turning to counterclockwise with height. These can support splitting storms with dominant right movers. There's other considerations with this shape that we'll get into. That change in the shape aloft, if you kind of make that a little lower, it does other things to storms. We'll get into the nasty details with that later. But let's ask this question here. Compared to the Hodograph 1 environment, how do you think storms would behave different in Hodograph 2, with everything else being equal? Any ideas?
I don't think they would behave much differently aside from the direction you're moving.
Okay, great. And that's because
The shape and size are exactly the same.
perfect. That's exactly it. How about this one? Which one would favor a right moving storm? Photograph 1, because what's that? The curvature, right? Yeah, the clockwise curvature. Exactly. That's it. Hodograph 2, which would also support right movers, but it wouldn't necessarily favor it because the straight hodograph is going to favor mirror image storms. So this gets at the idea that the synoptic pattern is important. If the vertical wind profile is what's generating these storms, then that's going to be associated with the synoptic pattern. So thinking about thermal wind arguments, warm advection, veering wind profiles, cold advection backing. So in this case, you could almost imagine what hodographs would look like at each location. So just quickly, what would you expect a hodograph to look like at B, point B? Clockwise, pretty big clockwise curvature. What about B compared to C? More or less curvature? More? Exactly, because you're in the stronger warm advection regime. And then A is going to be the backing wind profile, descent, stuff like that. So hodograph shapes can change over time. They can change over areas. This motivated, like Cameron said, using a hodograph map. You can see these changes spatially very easily. Another thing is hodograph shape can change quickly over time. So this is an example of a nocturnal low-level jet. We have the early evening transition. You get these really bowed out hodographs that you might be familiar with. But there's a lot of stuff that can change hodograph shape. Synoptic, low-level jets. We talked about warm and cold advection. Storms themselves can change hodograph shape. So just tons of considerations, but just keep in mind that looking at a static hodograph in time is not the way to do this. You got to keep up with the environment. So summary, the shape's related to the wind profile, no surprise there. The shape is what matters. It's not necessarily the orientation that affects the storm behaviors, all else being equal, which it's typically not. Straight hodographs favor splitting storms, clockwise curvature, right movers, counterclockwise left movers, and the synoptic and mesoscale pattern and features can influence the shape. Any questions with all that? All right, let's keep going.
Okay, now we're going to talk about storm motion, because let's say you're sitting here, a storm's initiating off the Wichitas, you got to figure out where the heck it's going to go from there. So what we're going to use is the hodograph to figure this out, because there's a lot of ways that we can predict or estimate the potential storm motions using just the hodograph alone. So you can see we got the mean wind there. We have the bunkers, right and left motion. We have the Corfiti vectors. We have, newfangled things like the deviant tornado vector. All these can be found using just a hodograph. So initially, a good approximation for the storm motion is going to be your mean wind. So let's figure out how to find that. All you're really going to do, right, it's in the name, mean, average. So don't make it difficult. We're going to take this hodograph here. We're going to find the average of the points around that hodograph, say from the surface to 6 kilometers or so. If we find the middle point, it's going to be ending up somewhere around right here. So that's going to be your mean wind for that straight hodograph. It's going to be a little bit harder on a curved hodograph. I'm not going to make you do this, but sometimes that mean wind could be off the hodograph, as we call it. And that could lead to a variety of cool storm behaviors like we'll talk about later. But what's fun is that supercells can propagate deviantly from this mean wind due to their internal dynamics. This is one of the coolest deviating supercell loops I think I've seen. Just parks it and then just rushes eastward with that dynamic kind of pressure perturbation, which we'll solve later. And so we can predict potential supercell motion using the bunkers method. So all we're going to do for this is we're going to find that mean wind that we found earlier. Then we're going to find the deep layer shear vector. So it's something from, about 0 to 6 kilometers. That's going to be your deep layer shear, like we talked about earlier, our bulk shear. So we're going to find that, and all we're going to do is deviate right and left from that shear vector by about 15 knots. And the original formula has it in meters per second, so that it's a lot more specific, but we're doing that translation for you here. So what we end up with, right, is our bulk shear vector, and then we're deviating from that by about 15 knots. In this case, the mean wind is probably about near stationary, because you can see both of these supercells emanating from that origin of the hodograph there. But storms can also propagate deviantly due to a variety of other factors. A lot of people like to just slap on a bunker storm motion estimate, and then storms do stuff like this. This is kind of the zippering method, right? When you're on a boundary, supercells love to kind of hog that boundary and zipper down it like this. Cold pools, right? QLCS motions have a completely different style here, and we can't really use the hodograph exactly to predict these. Corfiti vectors get at these somewhat, but these can be driven by cold fronts, etc., which really have their own motions. And then cell interactions, right? The famous Fujiwara, where you have two mesocyclones in really close proximity to another. All of these can affect supercell storm motion. So it's not just the bunkers motion. And none of these can be predicted by the hodograph. So just to keep you on your toes. Now try this. Where's the mean wind on this hodograph? Where do you think it is? What is our storm motion here? Yeah, so you're finding it on that hodograph, but what speed and direction does that mean when moving? Yep, perfect. Yep, you got it. So it's going to be plotted right around here and, north by about 15 knots. So now, who could tell me where the left mover is going to go? Yeah, you're going to add, well, okay, yeah, so I did a right mover. I can't read my own directions, it's fine. But yes, you're correct. So now, fun question. In this scenario, right, you got a QLCS bearing down in Davenport. You have some storm motion estimations, right, that your AWIPS is giving you. And these are going to be the bunker's right motion. Is this a good idea? No, it's not. This thing has its own motion. We're going to have to be really careful when we calculate or when we estimate storm motion of big systems like that. So in summary, initially the mean wind is actually a pretty good estimate of how updrafts are going to move. But as soon as they become supercells, we're going to want to use that bunkers right and left, or any of the other crazy things going on in that environment. Boundaries, convective systems, other cell interactions, these are all going to affect storm motion. So user beware. And now it's me again, lucky you. This is where we really start getting intense, right? Everything that we just talked about is kind of common knowledge. From this point onward, me and Harry are going to talk about some kind of new things, probably a lot of stuff that you haven't heard before. So now, right, when we've talked about hodograph shape and why that's important, when we have a supercell or a convective storm, the hodograph matters in relationship to that storm, right? It's not just the shape of the hodograph, it's how that storm is using it at this specific point in time. So what are storm relative winds? Well, imagine it's a really calm day, and you're in a car, but you're not moving. You stick your hand out the window, you're not going to feel anything, right? And maybe envision a little puppy hanging his head out the window. He's going to be kind of sad. But as soon as you start going 55 miles per hour down the highway, puppy's going to be happy. The wind's flowing, everything. So this is the difference between it could be a calm day, but you're still moving fast enough that you can feel winds. This is how storm relative winds work. So how are we going to find storm relative winds on the hodograph? Well, first you find your storm motion, which we did that successfully in our last lesson. So now we're going to draw our V, which is our wind at any given point on the hodograph. Let's try to find our 1 kilometer storm relative wind. And then this is our C, our storm motion. All we're going to do, the math behind this, is we're going to subtract V minus C. We're going to find that vector from C to V. This is our storm relative wind. This is the wind at a distance from that storm motion there. So to make this a lot easier, we're going to, so let's say then that you want to actually find the length of this vector and how strong that storm relative wind is. That's a little hard, right? You're trying to do the math in your head, right? How long is this vector? You're maybe trying to put it down here, lay it out on the origin, see how long that is. We don't want to do that. So the remainder of this lesson, we're going to actually shift our coordinate system to storm relative. So we're going to have our storm in the center of that origin, and then we're going to be able to count, say now we have 1, 2, 3, 40 knots of storm relative wind, because each of these range rings are 10 knots. This is going to make it a lot easier, so this is kind of what we're going to show you. So why is the storm relative wind important? Well, it directly governs the structure of a storm. Everything that a storm is feeling is from the storm relative hodograph. So we're going to show what this can do to your storm. Storm relative inflow is air in the lower levels of the storm that is kind of converging into the storm, right? If you think about like a 3D or a 2D, I guess, model of your storm, you got your big updraft here, air is getting sucked up from beneath, it's kind of going straight up in the middle, and then it's getting shunted out and ventilated outward on top. So you have convergence in the low levels, kind of non-divergence in the middle, and then divergence aloft. So in the low levels, what matters is your storm relative inflow, all that air feeding into the storm. And so this is actually, this can be used in a spatial sense where maybe you're trying to figure out of these two supercells, which has access to the most cleanest unstable inflow air. Well, if you have an inflow vector coming in from the east, like in this case, this is going to be your storm that has access to that clean inflow air, right? It's not always kind of the southern storm or the tail on Charlie that has the best access to that rich moisture. It's always a storm that's kind of leading with respect to that storm relative inflow. Whereas this storm is feeling all the air that this storm is leaving behind, right? So this is going to be a cold, gross, elevated mess. So let's take this example. This is actually a big supercell that was headed straight toward OKC quite a few years back. And this storm is anchored to a boundary. And let's say we have our hodograph looks like this, where our storm relative inflow is coming in from the northeast. Is the inflow air to the storm stable or unstable? Stable, yeah. And a lot of people think that, boundary anchored storms are really efficient tornado producers. But we know that the stable air mass is here and that air is coming from there. So this would really not be a good tornado candidate. Yes. Yeah. You must have listened to my talk last year. Yes, spoiler, we're not going to talk about that today. But generally that storm facing that storm relative inflow has the most moist, unstable, buoyant boundary layer and is better for tornadoes. But as he just said, the storm in the rear tends to be elevated sometimes, and that's when you can get a higher hail potential. But we're not going to go into those details today. Really good observation. So the fun starts when you start cranking the different speeds of your storm relative inflow. If you have stronger storm relative inflow, this is literally going to inject more mass into your storm at once. It can grow larger. Stronger storm relative inflow, that vector from your storm motion to those low levels, can make a bigger, stronger storm and can sustain one. And these bigger storms can produce more precipitation. So a lot of y'all think that, or have grown up to think that outflow has one of the biggest impacts on, if a storm becomes like high precipitation or low precipitation. And we know weak outflow to make a more HP storm. We're going to talk about that. But storm relative inflow can literally make larger updrafts that produce more precipitation. And that's how you get HP storms. Whereas, and this is kind of how your storm might look. I typically go by about 40 knots. If you got 40 knots of inflow, you could be dealing with a pretty powerful, large supercell. Whereas weak storm relative inflow, this is how you get mini supercells. I know that they tend to be called different things out in the plains. It's so dry, people just call them LPs. People end up calling them mini supercells out in the Midwest. They're generally the same thing, small supercells that don't produce that much precipitation. So this is when we have, say, especially less than 25 knots of storm relative inflow. I'm chasing this. This is a good day because this can give us storms that look something like this. So generally, this is important because larger storms are usually more hazardous. I'll add the usually there because this supercell was actually producing an EF3 tornado at the time. But it's always good to keep in mind, you know, is it going to pose a huge hail threat or wind threat? Probably not. So thing you've got to figure it out, which storm does Hodograph 1 go to? It's the left one. It's a smaller storm. Usually when you have a Hodograph this size, you're dealing with smaller supercells, unless you have a bunch of cell mergers making it bigger. It's just a lot harder to get a supercell this big from a Hodograph like that. So now we're going to go straight into the upper levels of the storm and talk about what that does. Storm relative outflow is where all this mass exits the storm and goes into the troposphere. So if we crank our storm relative outflow, you get these really long, stretched out supercell appearances. And they could be more low precipitation, right? You got that really LP hook. And in this case, you know, you got these really large rain-free bases. So yes, outflow does regulate the ventilation of precipitation. So even if the supercell is producing a lot of precip, if you have cranking outflow, that's going to be really well ventilated, and it's going to leave you a really broad rain-free base. So Hodographs like this are usually pretty good for spotting as long as you don't have intense storm relative inflow and HP storms. Whereas this is really what you do not want to be caught around, this weak storm relative outflow, less than say 20 knots or so. This is going to really, you know, that whole shear problem when your storm is tilted and you want your downdraft to be separate from your updraft. You're not going to get that in this kind of Hodograph. It's that outflow that matters. So when you have weak outflow, all of that precipitation from that updraft is just going to fall right next to it. You get these big, ugly HP storms, especially with a lot of rain in the RFD. Especially less than 20 knots or so is not really going to be a fun time for chasing. And you can even play with kind of the direction of your storm relative outflow. When your outflow is kind of in this multi-directional veered pattern, this can actually disperse precip fallout everywhere, inducing broader and more obstructive downdrafts. And actually, a lot of people think that, you know, veering and more veering is a really good thing, but excessive veering can really make a storm high precipitation. It can actually lead to these downdrafts that kind of disrupt the mesocyclone process. So in contrast then, when we have more unidirectional outflow, all that precip is kind of focused in this small sliver. You can see a big difference between this blob here and this neat little sliver here. And all that precip is headed off to the north of that updraft. These downdrafts are less obstructive. So especially if you had, say, a long track tornado ongoing, this is actually going to be a little bit cleaner and nicer for that tornado. So generally, less obstructive downdrafts are better for longer lived tornadoes. And so here's an example. Let's go with our supercell on the left here. What Hodograph, is it 1 or 2, that likely made that supercell on the left? 2. Yeah, and this was actually from quite near here. This was Bridge Creek tornado back in finals week, I think it was 2015. So the point being here, if my head is not in the way, this other Hodograph here is very infamous for making long track significant tornadoes. This was one on March 25th of 21, Centerville, Alabama. This is a Hodograph you do not want to reckon with. If you see this over Oklahoma and there's, you know, 2,000 Cape, head to your tornado shelter. So this is, yeah. So for a summary here, storm relative winds govern storm structure. It's not just the Hodograph shape, it's the winds that a storm is feeling from that Hodograph. Storm relative inflow can kind of affect a storm's size and how much precip it can produce, whereas outflow can kind of affect where all that precipitation falls, how obstructive these downdrafts are, and even tornado maintenance. And I'm finally done, and we're on to Harry.
Right. All right, so just keeping adding building blocks to this. Next, we're talking about horizontal vorticity. So first of all, who knows what horizontal vorticity is in the reference room of Hodographs? Okay, decent.
Our numbers are dwindling.
Yeah, okay, cool. Well, then this one will be a little more new. So how do we find horizontal vorticity on a Hodograph? We talked about how to find shear, bulk shear, storm motion, storm relative winds. Now we're doing horizontal vorticity. Well, let's first just think about the relationship between shear and vorticity. I think that's the best way to do this. So here on the left, we have an idealized wind profile with increasing westerly winds with height. We refer to this as a westerly wind shear profile, as depicted by that westerly deep layer shear vector in blue there. So with this type of increasing westerly winds with height, what we'll find is when we're trying to think about vorticity, we want to know how things are going to spin. So in this case, if you were to just put a pinwheel in this flow, somewhere right here, you'd notice that the pinwheel would spin clockwise like this. Does that make sense to everybody? So with that in mind, right-hand rule, physics, curl your hands in the direction. So it would be, for you guys, it would be like this. So you curl your fingers in the direction of that spin and your thumb points, in this case, where? Into the page. That's your vorticity vector. That's it. That's the relationship between shear and vorticity. So in this case, the vertical wind shear, westerly shear, induces horizontal vorticity into the page. You could think of these as vortex tubes or vortex lines with rotation about their axes, represented by that curling of your fingers. So horizontal vorticity is always going to be perpendicular and to the left of the shear vector, just from that relationship alone. And if you're not convinced, you can use the other right-hand rule, which for more mathematical types out there, you're just going to take the cross product of the unit vector k hat, that's the vertical unit vector, and the shear. So when you do this, your index finger points up or out of the page. It's a little funky in this example. Your middle finger points in the direction of the shear vector, and then your thumb is going to point in the direction of vorticity. You can kind of do this exercise on your own, but it's kind of just proof that this works. So going back to our original question, how do we find shear on vorticity on the Hodograph? Well, it should be pretty straightforward at this point. If the vorticity is always normal and to the left of the shear, and the Hodograph is just a plot of shear with height, then the vorticity is always normal and to the left of the shear, and therefore the Hodograph. Everyone good with that concept? Awesome. The stronger the shear in that layer, the stronger the vorticity. Again, they're completely linked. So in this case, you can see stronger shear in the low levels, corresponding stronger horizontal vorticity in the low levels. Let's do a question. Which one is correct? A or B? A? Great. Yep. Vorticity is always normal and to the left of the Hodograph. How about this one? A little more tricky. B? Not so tricky. There we go. Stronger the shear, stronger the vorticity. Now let's talk about streamwise and crosswise vorticity. So these are going to be the components of that total horizontal vorticity vector. To get at this concept, we need to consider the storm again. We're concerned about how a storm is interacting with the horizontal vorticity. So we want to compare storm relative winds to horizontal vorticity. Makes sense, right? It's what the storm's feeling. So that's exactly what we're going to do here. So we're just going to compare the pinkish storm relative winds and the horizontal vorticity. So for this first example, the horizontal vorticity and the storm relative winds are parallel to each other. They're aligned. Does anyone know what this is called? Streamwise vorticity, exactly. The both are aligned such that inflow essentially takes on that helical trajectory associated with the vorticity. This is the most efficient way for mesocyclone generation. We'll talk a little bit more about the details for that. This one, on the other hand, storm relative winds perpendicular to the horizontal vorticity. So they're crossing each other. The two are not aligned. Does anyone know what that's referred to as? Crosswise vorticity, exactly. This is going to be the least efficient way to generate a mid-level mesocyclone, but not impossible, and we'll show why. So let's just summarize this. The one on the left, streamwise, one on the right, crosswise. The idea here is that going back to shapes, the shape is going to influence this quite a bit. With the curved hodograph, you're naturally going to have a better chance of getting streamwise vorticity than a straight hodograph, at least initially. Because remember, storms are going to split off that straight hodograph and something's going to change. We're actually going to see a transition from crosswise to streamwise, at least partially. And we'll get a little more into that. So can you guys answer this question? Perfect. How about this one? Let me move me. B? Why B? Yeah, keep going. Yeah, why do you think it's B? I'd see a straight hodograph for both of these, so what's the difference? There you go. So the storm motion is what's giving us the change in crosswise versus streamwise in this case. Okay, a quick summary. The vorticity is perpendicular and to the left of the shear, therefore the hodograph. It's always the case. The stronger the shear, the stronger the vorticity. When the storm relative winds are parallel to the vorticity, that's streamwise. That's like throwing a football in a nice spiral. And then the opposite is when it's perpendicular to the vorticity, that's crosswise. And both the shape of the hodograph and the storm motion influence this, this streamwise versus crosswise vorticity. Okay, next, let's keep building on streamwise vorticity and SRH.
Yeah. Okay, so now that Harry taught you what vorticity is, now I'm going to kind of mess with your mind a little bit. So there's two ways to describe streamwise vorticity. How streamwise is this vorticity? Are we purely streamwise or not? And how much streamwise vorticity actually is there from this hodograph? So let's talk about this. Streamwiseness is how parallel that storm relative wind is with the horizontal vorticity. So in this case, I was trying to do a perpendicular first. In this case, right, we're parallel. Our storm relative inflow parallel to our vorticity. This is a purely streamwise vorticity. So we could say this is high streamwiseness. Here, this vorticity is a lot less streamwise, right? We're at an angle. So with more streamwiseness, if we're more streamwise, vorticity tends to be more aligned with the updraft, right? Updraft here, vorticity here, we're in harmony. And chasers actually kind of love this hodograph shape because this can yield more mothership style storms because your entire updraft is rotating. So I've found some of my best luck chasing these kinds of hodographs. And, you know, this is an example of what can come from this, right? You have a storm that immediately goes up, starts rotating, and just produces, you know, a couple tornadoes. You know, this isn't going to happen every time, but the more streamwise you are, the quicker this process can kind of happen. Whereas when we have more crosswise vorticity, when we're less streamwise, this vorticity tends to be dislocated from the main updraft. And so this is kind of as close of a picture as I can kind of get with this. But your primary updraft is here, and maybe a lot of your mesocyclone activity is out here. Your rotation really is not kind of aligned with that updraft. Your updraft is not exactly rotating per se in a lot of cases. So tornado genesis process might be a little bit slower. If you are weather weenies and have looked at radar enough, these Southeast US cases especially tend to have these really long kind of shearing zone style mesocyclones, right? It's not, your storm is not rotating per se, but it has rotation. It's really difficult for me to describe, but this is what you get when your vorticity is a lot less streamwise. Your updraft is not just immediately rotating. But the streamwiseness just doesn't tell the whole story, right? The magnitude of the streamwise vorticity is what matters as well. So how long this vector is here, how much streamwise vorticity do we have? So in this case, when we are purely streamwise, all of this vorticity, right, or horizontal vorticity, all of it is going to be streamwise. So this is how much streamwise vorticity we have. And, you know, if you know units of streamwise vorticity, 0.03 is usually a pretty sizable amount. Whereas, let's say our vorticity isn't very purely streamwise, but we have a lot of it, right? We have this really long, low-level shear, lots of vorticity here, but we're not very streamwise. So we're going to draw our component of streamwise vorticity. This is how much streamwise vorticity there is, given how long this vorticity vector is. So as you can see, we kind of compensate, like if we're less streamwise and we have stronger shear, we can still get the same amount of streamwise vorticity. So which of these hodographs has a greater magnitude of streamwise vorticity? C, yeah, it's the same length. And so of course you're not gonna, see the length of this vector in every hodograph you look at, but it's just nice to know that you can get vorticity in different ways. You can get purely streamwise vorticity and you can get not as purely streamwise vorticity and still have the same vorticity. And this is the easy one. With a greater magnitude of streamwise vorticity, mesocyclones can just be stronger and more persistent. Right? So there's usually not a drawback to having more streamwise vorticity if you're into tornadoes. So here's an example of a case that has very strong streamwise vorticity. You get, lo and behold, very strong mesocyclones. Whereas with a lesser magnitude of streamwise vorticity, when this shear vector is a lot smaller, mesocyclones are generally weaker and a lot more transient. So in this case right here, right, we have a supercell for sure, but our low-level mesos are kind of, disorganized, cycling, not really doing the thing. So compared to Hodograph A, which has that very purely streamwise vorticity, Hodograph B shows what? B, yeah. And it is kind of, the mind bending because we're using streamwise vorticity and streamwise, but they both mean different things. So in this case, right, we have a lot more streamwise vorticity, it's just less streamwise. So the magnitude of streamwise vorticity can be approximated using SRH, which is a product of the storm relative inflow and streamwise vorticity. So it kind of started as a way to kind of gauge the transport of streamwise vorticity into a storm. And it is the area under a hodograph. And you can kind of color this in, and right, this is an easy way to view it on the hodograph. So, and it depends on what depth we want to look at it, right? Let's say we want just 0 to 1, we do that, 0 to 3, we do something higher like that. So where does SRH usually matter? Well, usually in the lowest kilometer is most relevant for mesocyclones. There has been a lot of work that really found that SRH above the effective inflow layer just is not very relevant to this process. Vorticity can still be quite relevant above that layer for other processes, but especially for tornadoes, you're usually dealing with just that lowest kilometer. But when you're dealing with elevated storms, you generally want to look at effective SRH because that's going to kind of just give you the SRH above that pesky stable layer here. But remember that all measures of streamwise vorticity, including SRH, streamwise and streamwise vorticity, everything, depend on having the right storm motion. So most calculations of SRH, if you just pull up SRH on Pivotal Weather or COD or SPC, it's going to use that bunker's right storm motion whether you like it or not, and this is not always going to be correct. So what about this scenario? You have lots of 0 to 1 SRH, right? You have over 300, almost 400 SRH here, and you're forecasting a slow southward moving MCS. Do you think embedded tornadoes are possible with this hodograph? Yeah. Be careful when you use SRH, right? Don't just read off the SRH from a plan view. I should probably actually put a plan view map on here rather than a hodograph to ascertain my point. But yeah, you need to be careful to use the right storm motion. And we can't just, say QLCS tornadoes are possible given X amount of SRH. But also keep in mind, this is where it gets really messy. SRH is not just the streamwise vorticity, but it's also the strength of the storm relative winds. It's these vectors here. So I could give you 2 different hodographs here, each with equal SRH. And these 2 hodographs can have completely different magnitudes of streamwise vorticity. So if I asked you which hodograph would you expect to be most conducive to strong low-level mesos, but I told you each of these hodographs is exactly 150 SRH, what would you tell me? Yeah, it's better. They have the same SRH, but the left one is better because it has more streamwise vorticity. The other one, right, most of its SRH is being contributed to by strong storm relative inflow. So it's not exactly the SRH that matters, it's how much streamwise vorticity is there. Yeah.
So what if the one on the right that has more storm relative inflow, correct?
Yes, it does.
So like what you see is like the one on the right would have like a bigger updraft, but the Hodograph on the left is more efficient.
Yes. So, and if you, I'll analog this to a lot of Great Plains supercells have photographs like this one. They're quite big and they're not very efficient at producing tornadoes oftentimes. But let's say you have kind of a tropical system come in and you get these tropical mini supercells washing the shore. They're these really tiny things that are just furiously rotating. Like you have those little pinprick mesocyclones on radar. This is often what we're dealing with there. So it is oftentimes these smaller storms can actually have stronger mesos. They're just a lot smaller. So SRH, though, is very useful and a convenient parameter to assess the potential for these mesocyclones and tornadoes. And we've shown time and again that SRH is, you know, a foolproof way to kind of measure the potential of an environment to produce tornadoes. And right, you have a bunch of parameters like supercell composite or SIGTOR that are based off that Rich is in large part responsible for. But just keep in mind that streamwise vorticity and inflow strength can affect the storm in different ways. And so it's the components of this SRH that actually matters to forecasting. So for a summary, we talked about how the streamwiseness of vorticity can affect like how quickly an updraft acquires rotation. The magnitude of that spin in the atmosphere can affect how strong and persistent a meso can be. And that storm relative velocity is an estimate of the streamwise vorticity. And that was a mouthful. Now it's going to start.
All right, how's everyone feeling about all this stuff so far? Pretty good? Photograph experts? All right. The idea here, supercell dynamics, is not to scare anyone, any of that. It's really just to kind of piece all this together and think more physically what's actually happening. So we're basically just going to take all the concepts that we've talked about and sort of do a simulation that I'm going to call a story time. So the first thing, let's just kind of introduce pressure perturbations. So what are pressure perturbations? They're essentially storm scale highs and lows that are really generated based off the interaction of an updraft and shear. So you can get this idea that what we're really trying to figure out with all of this is the development of pressure perturbations, because this is going to drive everything else. So pressure perturbations can enhance or suppress updrafts depending on if the motion is directed upward or downward. And these gradients are always going to point from high to low. No surprise there, similar to everything else. So we're going to talk about two methods to generate pressure perturbations. This part one is going to talk about method one, tilting of vorticity into the vertical. And then we'll get into method two, which is updraft and shear effects. Both of these combined essentially describe supercell dynamics. For anyone that's math savvy and has seen these equations, method one is actually referring to the linear dynamics term and fluid extension. Method two is actually, nonlinear dynamics and fluid extension for number one, linear dynamics for number two, if anyone's interested in that. So we're going to do a story. We're going to sit back and listen to a story about an updraft and shear, and we're just going to see what happens when we do this. One caveat with this story, it does not explain convective mode, which might be a little confusing, but this story does not explain the development of supercells versus squall lines, for instance. You can have really strong shear and get a supercell in one environment, squall in the other. That motivates the idea that mode is based on an entirely different thing, but this influences mode. So just keep that in mind. We're just talking about how an updraft interacts with the hodograph. So let's start with a straight hodograph. So first part of the story, we have an updraft that develops. And what you can see is we have a straight hodograph on the right, and the initial updraft motion lies on the hodograph. That gives you what? Streamwise or crosswise vorticity? Crosswise, exactly. The inflow for the storm is crossing at a 90-degree angle the vortex lines. So they're not aligned. You don't get helical inflow into this initial updraft. But something's going to happen here with this updraft in the horizontal vortex lines. So focus your attention under the updraft and see what happens in step two. the updraft, the upward motion accompanying the updraft draws the horizontal vorticity into the vertical. That's known as tilting. And this tilting process, you can see these vortex lines and the associated rotation about their axes, they go from horizontal and then they start to become vertical through that tilting process. And eventually we actually get vertical vorticity. So tilting brings horizontal vorticity into the vertical. And in the case of crosswise vorticity, you can see that these vertical vorticity centers are flanking the initial updraft. They're actually on the edges with crosswise vorticity. And the one to the right is cyclonic. The one to the left is anticyclonic. It's simply based on the tilting of those vortex lines. Everyone clear on this so far? Makes sense? Okay, what happens next in this story? Well, these vorticity centers actually generate low pressure perturbations. Why is this the case? We have circular motion associated with these vortex centers. And in order to maintain that balanced circular motion, you need to offset centrifugal acceleration, which is outward. We need an inward directed force to balance that. How do we do that? Remove mass from the center of axis of rotation. That removal of mass gives you low pressures. So with that in mind, you get low pressure from anticyclonic and cyclonic vertical vorticity in this case. It's the spin that matters, not the direction of the spin. So we now have lows sitting aloft. These lows aloft literally act as vacuum cleaners. They suck air from below up into the vacuums, and that leads to updraft development. Upward motion flanking that initial updraft. You get upward motion that creates new updrafts flanking the initial updraft, and these new storms are now aligned with the the vertical vorticity and rotate. What this looks like on the Hodograph is on the right. You can see that that splitting gave you motions off the Hodograph, which gives you some streamwise vorticity that gives you some helical inflow. It's not purely streamwise, but this is what gives you splitting storms. Does that make sense to everyone? Anyone have any questions with this so far? Great. We get a nonlinear feedback process. The updrafts, these new updrafts that are correlated with vorticity, they strengthen the vorticity through stretching, and that stretching leads to stronger pressure perturbations or vacuum cleaners, which suck more air up, which leads to stronger updrafts, stronger vorticity, and it just keeps going. And the reason that this doesn't go on forever, which would be a question to ask, is that eventually storms can find themselves in excessively stable air and die, or convective outflow or destructive cell mergers can short circuit this process. Luckily, this does not go on forever because that would be scary. Now let's do the same exact story, the tilting of vorticity with a curved Hodograph, and see how this changes. So same thing, updraft develops, but we have a curved Hodograph. So what's different in this case? Streamwise, exactly. The inflow is now parallel to the vortex lines. That's streamwise vorticity. So when we get that tilting, what happens is the cyclonic vorticity is going to be centered on that initial updraft immediately. A way to think of that is that inflow became helical before it even got tilted into the vertical. So cyclonic vorticity centered on the initial updraft, anticyclonic vorticity displaced away from the updraft. We'll discuss that in part 2 of this, why that basically goes to die. And from there, same thing, low pressure perturbation induced in the vorticity center, but in this case, it's centered on that initial updraft already. We get the vacuum cleaner effect, but it's actually stronger because the vacuum is now co-located with the initial updraft, which is associated with stretching already. So you're getting stretching and vacuum cleaner effect, and you get a very strong dominant right moving storm with no cell split. So this is kind of what streamwise vorticity ingestion looks like in a kind of story sort of sense. So same kind of feedback process occurs, except it's much faster, much more efficient owing to that streamwise vorticity. Anyone have any questions? Okay, let's summarize it. Crosswise vorticity, storm split. After the split, storm motion off the Hodograph requires some rotation due to the updraft being correlated with the vorticity, and the updraft strengthens. Streamwise vorticity, no split, immediate updraft rotation. Okay, let's do some questions and see how everyone is understanding this stuff. So the tilting of crosswise vorticity results in which one of these? B? You got it. Rotation develops on the flanks of the initial updraft. Why does streamwise vorticity support immediate updraft rotation? Exactly. The vorticity is already aligned with that updraft due to the streamwise vorticity. Where is the significance, excuse me, what is the significance of low pressure perturbations aloft in rotating storms? See, exactly. This is a dynamic effect. It's a vertical perturbation pressure gradient force that literally is dynamically forcing air upward. So significance of this is supercells can often lift parcels with more sin than you would expect, inhibition, than disorganized type storms. Okay, this is part 2. This is going to talk about the updraft and shear. This is the other way to create pressure perturbations. This is the linear term of pressure perturbation equation. So same thing that we're trying to figure out here is the development of pressure perturbations, the storm scale highs and lows, and how they influence updraft strength and motion. Method 2. Let's jump right into this. So on the left, we have a westerly shear profile that we showed earlier as well. Put an updraft in that environment, and what happens? So let's think of this in like a mass continuity sort of perspective. So think of this updraft as a log in a stream. And as the water kind of impinges on that log, you're going to get a buildup of mass on the up shear side of that log, and then a deflection of flow on the down shear side. That's going to give you a mass buildup or a high up shear of the updraft and a low down shear. This leads to that dynamic lifting effect down shear of an updraft and subsidence up shear of the updraft. That low, it's the same thing. It's a vacuum cleaner. It's a low sitting aloft that's going to suck air upward from below. So that's the conceptual model. You have a shear vector impinging on updraft, and low develops down shear, high up shear. So this is, let's start with a straight hodograph and see how this works with an updraft. So with the straight hodograph, the shear vectors are in the same direction through the entire profile. So what this gives you is simply the conceptual model. It's low pressure down shear of the updraft, or to the right in this case, excuse me, not right, just, yeah, that gets confusing. Right is actually toward us out of the page in this case. So low pressure down shear, high pressure up shear, and that drives dynamic lift down shear. This effect is strongest where the shear is strongest and the updraft is strongest. So in this case, you could assume that that's going to be somewhere aloft where the updraft is strongest, but the shear profile matters. That can really complicate things. So this is the ideal scenario. So you get dynamic lift down shear, subsidence up shear, but to the right or left of the hodograph, that's out of the page and into the page, there's no upward or downward motion enhancement. So the expectation of left and right mover development to the left and right of the hodograph, neither are enhanced or suppressed by this effect. It does not affect left and right movers with a straight hodograph. This is why we get mirror image cell splits with this process. They're equal opportunity, essentially. Neither enhanced, neither suppressed. This changes a lot with when you put a curve in the hodograph, especially when you do a full concavity or a half circle hodograph. Let's see what that looks like. So in the low levels, in the pink sector of this hodograph, you have a south to north shear vector impinging on an updraft in the low levels. That's going to give you a high to the right of the updraft in the low levels and a low to the left in the low levels. Then in the mid levels, you have, similar to that straight hodograph, up shear and down shear, couplet of high and low. And then in the upper levels of the hodograph and on the updraft, you have a low that develops on the right side aloft and a high to the left. I know that's a lot. Can you guys visualize this pretty well? Does this make sense? Awesome. So what does this do? We're stacking pressure perturbations on top of each other in this case. So to the right of the updraft, we have high in the low levels, low aloft. That drives an upward directed vertical perturbation pressure gradient force, which enhances the right mover or any motion to the right of the updraft. That's on the concave side. And on the other side, it's high over low. So it just drives down that dynamic downward motion. This explains why in that case, that cyclonic vorticity, they got shoved away from the updraft and didn't actually induce new updraft. This effect can actually suppress any motion, any development with downward motion on that side, on the convex side of the hodograph. So this is what this might look like. You could get right movers enhanced, left movers suppressed, and oftentimes you see no cell splitting with this. So takeaway, the updraft is enhanced on the concave side of the hodograph and suppressed on the convex side. So typically that's going to favor the right mover and suppress the left mover. Exact opposite with a backing wind profile and a counterclockwise curved hodograph. It would actually enhance the left mover and suppress the right. We already talked about why that's not going to be as common in the Northern Hemisphere, as that's associated with descent on the synoptic scale, essentially. So the second takeaway from this is that these pressure perturbations induce additional deviant motion or propagation. We showed that cell splitting in method 1 led to deviant motion off the hodograph just due to that cell split. With a curved hodograph, we already said we might not get cell splitting. So what's driving propagation? We know that right moving supercells still turn to the right. It's this effect, actually. It's the upward motion on the concave side. You literally get new updraft development into that dynamic ascent. So that's why you see a clockwise curved hodograph, new updraft development into that area of ascent. And again, we're going to use the right mover storm motion for this estimate. If you had a counterclockwise curved hodograph, the opposite, you'd use the left mover. And with a straight hodograph, you use both because of the cell split. So takeaways here are that larger, stronger storms can deviate more. Again, we talked about this effect is maximized where the shear is strongest and the updraft is strongest. Stronger, wider, more persistent updrafts are going to deviate more to the right. You can see that in this rotation tracks. Stronger rotation track there deviated much more to the right than these weaker ones circled in blue. And so this kind of motivates the idea that you can change these shapes with height and enhance the right mover in one level, suppress it above that. So Cameron's going to get into this next and talk about some of the nuance with this. It's not as typically as straightforward as just saying, oh, it's suppressed because we have this counterclockwise curve. It matters where it's happening, is the long story short. So let's let Cameron talk about this with us, and this is going to wrap it up.
Save you if you were okay, so we can get some really tricky shaped photographs, right? We talked about our N-shaped or our I think my favorite is an SPC Outlook a long time ago. Rich might know who this was, but the wretched J-shaped photograph. That is my absolute favorite. And yeah, maybe this is a wretched end, but when the point is, like, when we can get this subsidence or this suppression for a right moving storm, a lot of people quickly jump on, oh my gosh, veer back, this is gonna harm our supercells, whatever. When should we actually worry about dynamic suppression? When is this actually something that we deal with? Well, to make it easy, we're really only going to worry when this dynamic suppression or when this inflection in the hodograph is within the effective inflow layer, because the effective inflow layer is where the storm takes in most of its air. So this is kind of going to be our rule of thumb for this. So if you look at, say, usually the effective inflow layer is between 0 and 3 kilometers. So I'm just gonna highlight these points here. It's not always going to be within that layer, but I'm going to make this easy by just highlighting these. So in the left hodograph, you see that the entire effective inflow layer has a nice broadly curved hodograph. That's good. We don't care about suppression in this case. This hodograph on the right, though, has the N entirely within that effective inflow layer. This is no good, no bueno. So when should we actually worry then? If you see a hodograph that looks like this, and you have, veer back, veer, this doesn't actually matter because the shear is not reversing direction with height. This would only affect, or this would only suppress a storm if that shear went back down again and then back up. So this case is completely irrelevant, right? We're not, there's no suppression here. This case, you know, we do have this, but it's well above that effective inflow layer, right? This is well above, say, 4 or 5 kilometers or so. So this is really not something that we should be worrying about. This case, we're kind of, you know, we're not ideal. We have this big inflection and it's right above that effective inflow layer. But remember, there's more frameworks going into this. We have a lot of streamwise vorticity here, and that low is 0 to 2 kilometers. We're good, right? We don't really have to worry with this Hodograph. No, it's not the best at supporting a right-moving storm, but we can actually get some pretty long-lived tornadoes with this kind of Hodograph. The ones we do need to worry about, again, I'm just going to show this one over and over again, is this one. Look how wretched this is your wretched J. This is look at this. You have anti-streamwise vorticity here in that 1 to 2 layer, right? This is your streamwise vorticity, your vorticity vector pointed this way. This is your anti-streamwise vorticity pointed that way. You don't want to see this ever. So knowing this then, which of these photographs should you be most concerned about dynamic suppression? Number 2. Yeah, I mean, look at some of these. These are weird shapes, right? But these aren't actually all that bad. It's this one. I've almost called this like an awkward llama Hodograph. Like it's just, I don't know how to describe it. It's just, it looks really awkward. And so now, which Hodograph could support a severe left or okay? Wait, yeah, this is hard for you in the audience. How many of these Hodographs here could support a severe left moving storm? How many? Yeah, I'm hearing 2 or 3. All these 3, right? All of these you can get left movers from these Hodographs easily. There's not enough low level shear here to really minimize the potential of left movers. And so this does actually surprise a lot of folks, especially with Hodographs like this one. But you know, just because you have that little bit of curvature here, you can still get some raging left movers with this. This is probably most favorable, and this one probably coming in second. The fact of the matter is, you probably are not going to see many left movers, especially not severe left movers with this Hodograph here. Now, a little bit trickier. Which Hodograph is least favorable for right moving storms?
First and last.
Yeah, raise your hand for first. Raise your hand high for first. Raise your hand high for second. Or last, sorry. It is the last. And this is tricky. You actually, and I put this in here because I actually love these Hodographs. This is these are really common on the high plains, especially near the Black Mesa. These routinely yield strong right moving supercells. And it, you know, just that little flip back here makes it look really awkward. And I've had a lot of people think this is their answer to this one. But it's really this one. I mean, look at how big that concavity is for that left moving storm. We just have a little bit of right moving shear. We have that little hump here, which makes it look like a right moving Hodograph. This is really more favorable for left movers. Now, wrapping all of this and every lesson together, which Hodograph do you think is most favorable for an outbreak of long, strong track tornadoes? We had some gut reactions and then some reconsidering. Raise your hand for first. Raise your hand for third. Ooh. I'm gonna go with this one. There's a little bit of subjectivity here, but think about it. We got really strong low level shear, lots of streamwise vorticity in that low levels. This Hodograph could never, right? Tornadoes are going to be a lot easier with this. We have that backing aloft that's not really going to be suppressive of right movers. And we have that backing aloft, which could actually help sustain a tornado, given latest research.
You can definitely get strong tornadoes.
Yes, you could. There has been many cases of strong tornadoes with this one. An outbreak of many strong, long-lived tornadoes is a bit less likely with this Hodograph. All right, we'll switch it up again.
This is it, right?
Yeah, I think so.
Okay, so we finished this entire thing with a quick case study to piece all the concepts together. So let's take a look at this. So it's 21Z in your CWA that you're responsible for. It's actually, here's the Pueblo CWA. You got plenty of buoyancy and storms are initiating on the high terrain in the left side of this big box here. And I'll just give you a hint that forcing for ascent is not overly strong. It's modest. It's enough for storm development. What do you expect from this initial storm activity?
So, initial basically going to be like individual cells that usually kind of deal later.
So just to help you out a little bit here, so focusing on the shape of the hodograph, which has been this whole lesson, we're not worried as much about, you know, everything else regarding mode necessarily, just based on the hodograph. What do you think? Yeah.
Maybe Taylor, maybe it's there, but yeah, a little bit of a fix that you find that crosswise with this guess that you have definitely more crosswise in like the middle left or say that lowest shear is kind of medium. So I say that I would prefer maybe split.
Okay, so you're going with B?
Yeah.
B? Okay, yeah, that's a great answer. So the idea here is that this, you know, the hodograph here it's really more straight. You know, the way you can tell this also is look at the mean wind, which is the square. And this is why we love hodo maps. That square is on the hodograph. So if that's your approximation for initial storm motion, and it's mostly straight in that layer, then that's where the hodograph, that's where the storms are going to be. That's crosswise vorticity. That goes back to the conceptual model. We get tilting and splitting, and that's what this is going to favor. So, so that's what this looked like here. We got kind of a messy looking mode at first. Clearly Supercells, lots of big hail reports with this, but a lot less confidence in a supercell tornado sort of event with this initial activity. Okay, let's move to 23Z. You're examining forecast photographs, and something's changing here a little bit. What do you expect to happen with this storm evolution over the next couple hours? And another hint here is forcing for ascent remains constant. So we're not expecting a giant, you know, derecho to move across. C? Okay, why C? Yep, big half circle favors the right, enhances the right mover. Streamwise vorticity increases, splitting dissipates everything that would favor dominant right movers, less cell interactions, and a higher tornado potential, all else being equal. And that's what you see here. You see really these left movers start to fizzle and right movers become pretty dominant. And then the last piece for this is it's 0Z now. The cap is setting in. It's getting late. Sin is starting to increase to some concerning levels in some locations. What do you think will happen next? B? Why? You got it. That's it. I couldn't say it better myself. That's perfect. And what we see is supercells continue on into the nighttime. And just to summarize this, you can see it played out that way. You had initial splitting supercells, large hail, transition more to a dominant right mover supercell tornado event in the far eastern areas. And then this is a summary page that I put together a couple of years ago that's may or may not be available for you. And that's it. Does anyone have any questions on all that stuff? I know that was just a ton of material.
Thank you guys so much for being our guinea pigs.
Yeah, seriously. Hey, everybody, hold on one sec. Could you repeat that?
The one where you compare some four photographs and a lot of it has to split between one and two. What was the limiting factor in one that makes it collect? I know why it be stable. What was the limiting factor?
I know which one he was talking about. Yeah, so this was a point of contention. So really, out of all these four, most favorable for an outbreak of many long-lived tornadoes. And out of the concepts that we talked about, right, how to get a strong, long-lived tornado, you're going to generally be more favorable with stronger low-level shear, more streamwise vorticity. So in this case, our vorticity is streamwise, but there's not a lot of it. There's not a lot of streamwise vorticity here in the low levels. Is the rest of the Hodograph amazing for huge supercells everywhere? Yeah. I personally have seen this result in kind of a massive mess of lots of supercells that kind of occasionally produce strong tornadoes that cycle rather quickly because we really don't have the low shear to support that.
So a lot of your
Yeah. You could argue that, yeah. So if you go, yeah. Oh, your discretion.
No,
You had a question, yeah.
Bit of a related question. So, what part of the Hodograph really determines if the storm's going to be more long track or cyclic?
Yeah, so that's actually something that I'm working on right now. And spoiler, it's the lowest kilometer, like always.
So I always thought it was more the mid-level shear, but then like I've seen cases where it's like you can tell there's no low-level shear because the storm cycles every 60 seconds.
Yeah. It's I think I would say a primary effect, at least that we're seeing, is in the low levels, but the upper levels have at sometimes like a comparable effect. And we have to, note, like, are we veering? Are we backing? Usually our backing is slightly better. And that's counterintuitive.
And then one more question. When you're talking about dynamic suppression, does that have any link to how RFD is created?
It does. Well, yeah, so if you have like a high pressure in the rear of a supercell, that can help force an RFD. Yeah, that's a good question.
I've never heard like what actually causes it.
Yeah, well, I think we're learning now it can be caused by not only the supercell itself, but by its friends, cell interactions. But on a supercell basis, yeah, the pressure perturbations are going to matter a lot. Okay, we have, let's do you first. I think you had your hand up first.
Would the second photograph here be supportive of those like small mesocyclones that spin up quickly and then just die after a few minutes?
Yeah, this is actually a really common cold core mini supercell Hodograph. I actually really like chasing these tornadoes galore, just not an outbreak of strong long track tornadoes. Yeah.
Is the transitioning from the storm following lean wind to then right movers, is that the reason why storm structure tends to delay from looking more just like a cumulus updraft to the structured piece that you get later on in this fight?
That and the sin, I want to say. Yeah, but I think both of those kind of in tandem. Like I've seen some really yucky, like cranking right mover storms that just didn't have like, the sin and dry air, but I think it is both. And you had one more.
How you mentioned dynamic suppression and does that also connect to like planking line precipitation, whether dynamic suppression kind of forces some of that precipitation to fall behind your updraft, or is that a different process like planking line precipitation?
It's kind of hard to isolate all of these things. I mean, there's a lot of different contributions. So there's going to be convergence associated with that trailing boundary that can lead to storms. Maybe there's a lot of sin, maybe there's not, maybe there's a strong downward motion there. So I'd say the answer is, it's tough to say exactly what's driving it, but it speaks to the complexity of all this stuff.
When you get to the rear flank downdraft too, you also have to think about what the storm, this rotating updraft, is doing to the precipitation that you mentioned. How big is it? How strong is it rotating? How much precip are you forming? It's a mess trying to cleanly separate these things out.
Another question, so like so kind of two questions here, so like that dynamic suppression, that dynamic lift, is that what help drive like meso handoffs where you have a new updraft developing south of a storm and then it takes over?
We're just having this conversation the other day. Yeah, I think it's reasonable to assume that, you know, with more curvature, you're gonna get more of that upward motion enhancement on the concave side, and maybe more propagation into that, or even more propagation than you would expect, right?
Yeah. I think a theme throughout this is that excessive veering isn't actually fantastic for strong long-lived tornadoes.
Then
So
related question, if you have an updraft itself that is like really strong, could it also suppress that like formation of new updrafts through that dynamic lifting too?
Can you repeat that?
Like if you have an updraft that's really strong, could that strong updraft itself prevent new updrafts forming from that dynamic lift?
I'd say it just depends on the shape of the hodograph. I mean, if it's a very clockwise curved hodograph, you're gonna get more of that dynamic suppression effect versus a less curved or straight photograph, where there's really no motion from that second dynamic term.
So when you get like Supercell in bed with like ULCS in particular, like the Mormon Supercell that the Mormon Supercell, was that kind of what created that gap in the line? Was that the dynamic suppression with that embed Supercell? Because there wasn't really precipitation directly south of it. Is that why you kind of got that gap, those gaps, and you have embedded Supercell with ULCS setup?
I couldn't tell you.
It's a good question. I mean, I think there's a lot of things that can contribute to, it gets a little complex when you have a strong outflow boundary and just strong baroclinic zone associated with the outflow boundary like that. Things get a little complicated because you have vortex sheets along that baroclinic vorticity zone, and those vortex sheets tend to kind of disperse into small vorticity centers, which can give you gaps. So I'd say it's tough. Do you have anything to add?
Yeah, well, that specific case, you're talking about February 26th, the tornado formed right by the building. That storm, I mean, there were tremendous changes going on the like 15 to 30 minute time scale. So there's so many moving parts in a case like that. I don't know that I would be comfortable saying that attributing a gap in the line to any one particular thing. That was incredibly complex.
That line, that meso that was associated with that future tornado, that was there. It was embedded in the line. It was there along. We call that a supercell line. And basically all those dynamic effects, that lift associated with the meso, the vacuum, and then strong lift along the color pool, all that stuff actually, basically, it allowed the mesocyclone to utilize the whole hodograph, going back to what Cameron said. So you end up starting to lift parcels from lower and lower, where that was a ginormous hodograph. So if you start to lift parcels closer to the surface, then you're talking about a lot of streamwise vorticity, a lot of stuff that pushes it into the supercell category. So yeah, tough to say what exactly is driving it, but that would be my argument.
Okay, so this is something I've noticed in a few simulations I've run, and I want to know if it's realistic. Whenever the updraft gets above the LFC, it's just yanking air from the lower levels up into it. Do you ever get sinking around the updraft as a mass response sort of thing?
The sinking around the updraft is probably more related to the RFD development and all of that stuff. I mean, again, so it's hard to separate these things completely. That's what I would say.
In that simulation where you're also dealing with evaporation hydrometers now, and you're dealing with other storm scale processes as well. If you're not going to be able to relate that to just like the photograph and the linear and nonlinear perturbations. There's just too much going on so much small scales. This is all environment. There's nothing about what the actual story is doing to an environment as well. That's part of that. And that's another thing that we're in that.
But like on a broad sense, right? Like what goes up must come down too. So like usually, like people say, like as soon as the supercell really starts getting going, like the subsidence around it starts squashing other things. I don't know how relevant that is, or if it's also based on the shape of the hodograph. It likely is. But yeah, it's likely that you could see broad subsidence where there's precipitation at least.
But again, whereas through mass continuity, where's most of that subsidence occurring? It's not down low. It's way up high. So how relevant is it? You can probably come up with a scenario if you put it the right sounding, the right Hodograph shape.
Right.
Whether it matters, doesn't matter, who knows? That's what makes it fun.
Yeah. Any last minute questions before we move on?
And I just want to say, like, the questions that y'all had, like, really made me feel confident that, like, you learned a lot tonight.
Yeah, very.
Or there is some good stuff in here.
All right, I think we're gonna go ahead and get started and try and hurry up so you guys can get to listening to Rich talk instead of me, because that's gonna be the more exciting stuff. This is a little bit more storytelling, a little bit of history, a little bit of current state of what's going on, a little bit of what's in the future of research. I'm gonna try and cover as much of it as I can. Yeah, so if you have any questions, you can feel free to interrupt as we go. I'm going to try and keep this on the shorter side, and we'll see if that happens. So my name's Kelton. I work at SPC as well. Went to undergrad here not too long ago, although it's getting further and further away by the day. So it'll happen to you too. Don't laugh. We're going to talk about supercell tornado genesis. And so this is a natural follow-up in that Cameron and Harry did a great job of describing the environment and how the Hodograph plays a role in that. But there's a whole nother world that happens on the storm scale. Where does the vorticity for a tornado come from on the storm scale? Any ideas? Yeah.
Storm itself is big for much of that.
Yeah. So like, would you say from the mesocyclone, from the environment, the shear being, the vorticity being amplified from the environment, or is it?
Part of it, but it's a combination of, vorticity brought to the surface by the cold pool, the amplification of pre-existing environmental vorticity, and probably even Coriolis.
Yeah, so that's the idea I want to get across. There's all these different areas of vorticity that you can really aggregate underneath an updraft, and we're gonna kind of explore what some of that looks like. So if the keyboard decides to work, maybe we will go next. Okay, cool. So the idea is to just kind of have a history of tornado forecasting science and the iterative process between forecasting, collecting observations, and running our numerical models. And there's this kind of feedback process and loop that happens as we advance our understanding. And then some other key points are kind of the current state of tornado science, the role of downdrafts, and the importance of strong low-level updrafts in tornado genesis. The disclaimer, though, is I can't qualify myself as an expert yet. Dissertation's not finished, but even if I was, a lot of this knowledge is still evolving and new, and it will continue to evolve and continue to grow. You'll never stop learning new things, and so this is kind of meant to reflect that. The papers referenced are a great resource for more depth, but they're only a subset of the rich history and literature on the matter. So I would definitely recommend taking a deeper dive if you're interested. Some of this contains some opinion. Always check opinion against the body of established literature. Don't take what someone says just at face value because of some interesting and cool visualizations. But I think most importantly, the atmosphere doesn't really care about our conceptual models. They're really more for us than for anything. And so the more you can get comfortable with breaking the boxes you build to help you understand stuff, the better of a time you'll have going forward. But who knows about the first successful tornado forecast? All right, good. So some of you do read up on your history. It's good to know where you came from, and especially when you're in this building and the rich history that we have with tornado science. It's a fun. It's not only a fun story, but you can learn a lot about the process. So Major Ernest J. Fawbush and Colonel Robert C. Miller were meteorologists stationed at Tinker Air Force Base. And in 1948, a tornado struck the Air Force Base and caused a significant amount of damage. The general did not like that very much. It was very expensive and obviously not with much warning. And so he tasked his meteorologists in the days after to analyze data and try and come up with a means of predicting this in the future. So over a period of about 4 or 5 days, they noticed that the pattern was looking pretty similar to the last tornado. Who, after 5 days of hand analysis, would feel comfortable making a forecast for tornadoes?
Just Rich.
Like, just think about that for a moment. Like, there's even a full 100 years of history of tornado science that was kind of squashed in the 1800s because of fear of hysteria. So you've got this idea of it being taboo, and then suddenly your boss being like, hey, tell me if there's going to be a tornado today, and worrying about your job being on the line. So that's a lot of pressure.
And they were pressured multiple times on that day by the base commander to issue a forecast of some sort. And so finally, they just threw their hands up in the air and said, yeah, we think there might be tornadoes today, and left work thinking that they weren't going to have a job the next day. 6 p.m. arrives, and lo and behold, there's a tornado. How many of you would even feel comfortable issuing a tornado forecast before convective initiation? Right? Like it's kind of absurdly lucky that this even worked out the way it did. If you dig into it, it was actually a storm merger that happened before reaching Tinker Air Force Base that most likely resulted in producing the tornado, which is just, again, not something that they could have anticipated or predicted at all. But it kickstarted what would eventually be it would break the half-century ban on forecasting tornadoes. And in 1951, the Severe Storms Forecast Center at Tinker Air Force Base was established. It would go through many renamings and eventually become what is now the National Severe Storms Laboratory and the No Storm Prediction Center upstairs. That's why we're all here today, right? Because on some level, we've been interested in this stuff and had heard about what goes on here and the rich history and cool people like Rich that work at SPC and help advance the science while also forecasting it. So that's why I like to include this little bit of history just in case some of you aren't familiar with it, because it's, I don't know, I find it neat. But we get into the 60s through the 80s and we start coming up with some theories for how tornadoes form based on observations of supercells, and this cool thing called Doppler radar starts showing up. We start collecting observations and mobile vehicles and start trying to put together a picture of what's going on. And so Lemon and Doswell 1979 was kind of the first attempt to not only aggregate other studies people had done, but incorporate radar observations into that in order to come up with the first conceptual model of the supercell. The term supercell actually comes from a British scientist named Browning. I can't remember his first name. So that's where the term came from, but this was the first paper that really, one, put forward the concept of the rear flank downdraft as being an important part of a supercell, and then two, kind of did an overview of what some of the different mechanisms of tornado genesis could be. And so we're going to kind of go through some of that thought process in the paper and see things through their eyes. And so one of the pieces of the paper is kind of this ugly looking equation stuff that, you know, it really isn't too terribly bad, but you take it term by term and you go, okay, well, how can I get vorticity? And then how can I amplify it, tilt it, stretch it, and what in a supercell might contribute to those things? So I'll just summarize. They kind of hypothesized that convergence of existing vertical vorticity was a questionable tornado genesis mechanism to them, because to them, tornadoes were associated with updraft weakening in radar observations. So like, well, if the updraft is weakening, then we're probably not going to be relying on low-level convergence as much. The low-level gust front along the forward flank was suggested as a possible formation mechanism for vertical vorticity due to the roll-up of shear vortices along the vertical vortex sheet. But Lemon and Doswell eliminated this specifically due to Doppler observations of elevated tornado vortex signatures. To me, this is a really interesting point. I think I mentioned a little bit later, but that was them trying to correlate their observations with their conceptual models. Scale analysis was used to reason that vortex tilting and stretching should clearly be candidates for generating vertical vorticity as well. And that baroclinic vorticity generation could be important, but at the time there were few thermodynamic observations near supercells. So we didn't really know whether or not this baroclinic term from the temperature gradient from the cold pool to the inflow, whether or not that really mattered as much. So this is just kind of some of their thought process and what they put forward. And then they also put forward this cool 3D model of what the updraft, forward flank downdraft, and rear flank downdraft look like. And this idea of the tornado vortex descending from a loft at the interface between the rear flank downdraft and the updraft. And so I don't know if the mouse will show it, but there's like a little tube up here that they kind of show descending as the rear flank downdraft descends, and then that being responsible for the initial vortex. So this was kind of the state of the art for a while. And just to show, I mean, like, obviously, I think you guys all know what a reflect downdraft looks like, but when I put these slides together for a different class, it wasn't, there weren't as many severe weather weenies in there. So, but still a good example of the visual features that you see associated with supercells. So just to summarize that, the main thing that they put forward was that the rear flank downdraft was a likely and important mechanism for tornado genesis. Part of this was because of its proximity to the tornado, or tornadoes they studied and the visual evidence they had from storm chasers and photographs and videos at the time. But the vortex tilting and stretching could also be important. Baroclinic generation was kind of an unknown, and they really ruled out this whole idea of the forward flank downdraft gust front area being responsible because of this whole elevated tornado vortex signature thing. Turns out it was an artifact of radar scanning strategies. Yes, question? What years? This paper, I think 79, sorry. I should know that off the top of my head. But really that elevated tornado vortex signature was an artifact of radar scan strategies. And it turns out several decades later, once we get things like sails and mobile Doppler radars and stuff, it's pretty well agreed upon that tornado vortex forms in the lowest portions of the storm. So I leave this in here because there's an entire mechanism of generating vertical vorticity that got ignored for quite a while because of this line of reasoning. So always check your assumptions, make sure that it's backed up robust. This isn't to knock Les Lemon and Chuck Doswell. They're way better than I will ever be at anything. But it's to get across the idea that our conceptual models can sometimes be our own limitations and downfalls whenever looking at these problems. Sure, get back to that. So now I'm going to fast forward several decades and skip a lot of cool research in there as well. In the 70s and 80s, we get the invention of cloud models, Weinman and Clem finally starting to simulate supercell thunderstorms and getting the dynamics of splitting supercells and low-level mesocyclones, but still can't really quite tackle the tornado problem just because of resolution up until the modern era. So the standard for quite a while has been Markowski and Richardson 2014. And this is a numerical model study. And numerical models are fun and neat because you can tweak all these little different knobs and hold other things constant. And you can remove certain assumptions and problems that are too complicated to deal with right now and say, well, if we just simplify the problem and see how we get tornadoes this way. And so their version of simplifying the problem was to use just a dry heat source and heat sink, and there's no precipitation whatsoever at all. So you have ascending air, ascending warm air and descending cold air. They vary the placement of the two next to each other and the strength of them. And we're not going to go through all of them, but by varying just these two things, we're able to come up with some very interesting tornado genesis scenarios and mechanisms. But the main thing to take note of is there are no moist processes, no latent heat, no hydrometeors, nothing, just the heat source and heat sink. What they found was that low-level horizontal vorticity from the environment, low-level horizontal vorticity in the ingested by the updraft was primarily generated by the baroclinic mechanism. So by your thunderstorm outflow. They found that strong low-level environmental shear resulted in stronger mid-level mesocyclones and therefore stronger dynamic lifting by the mesocyclone. So this is kind of your right mover, curved Hodograph type situation. You're really strengthening that mid-level mesocyclone with that environmental vorticity. And then that combination of strong dynamic lifting and the weak negative buoyancy from a particular cold pool configuration, they found provided the best combination of factors leading to tornado genesis. And the critical finding was that the downdraft was critical for reorienting baroclinically generated horizontal vorticity into the vertical. And then that was what was being stretched and amplified underneath the low-level mesocyclone in this toy model. So the figure on the right, you'll see a red line. It's kind of an ideal parcel trajectory that starts near the interface of the inflow-outflow boundary, kind of goes up and over, and then descends down underneath the downdraft, and then enters underneath the low-level mesocyclone, gets tilted and stretched into the vertical and becomes the tornado vortex. And then, again, they varied a lot of different things in the study, including how strong that cold pool was. So basically how hard is it to lift those parcels into the updraft, and also how strong the updraft is and how far away from the ground, basically. And so with that, you get some really interesting parcel trajectories that you can track through it. So these are some idealized lines, and you have the time to tornado genesis. This is actually pre-tornadic vortex for the entirety of the parcel trace. And you see that this pre-tornadic air is largely, again, interacting with your outflow boundary, descending, and then getting tilted in, up, and out the updraft. And you can also see the updraft is kind of slanted a little bit and descends towards the interface of the inflow and outflow. And then that's what's drawing those parcels in up and out. Then we switch to, I think this is, yeah, T-5 minutes. So you see these yellow lines right here. These are vortex lines, sort of in the rear flank downdraft area. I think if I remember correctly, this figure is mostly showing how you can reorient these vortex lines into the vertical and start aggregating vertical vorticity that way. Versus the environmental vortex lines, or those blue ones kind of more in the mid-levels, if I'm remembering correctly. And the idea being that you can kind of connect through what they call vortex line surgery. You can connect a surface vortex line with the main updraft, and then that's how you kind of route the vortex down in the bottom. There's a whole hour's worth lecture just on the physics of this stuff that I'm not going to go into, but it's pretty interesting stuff. And then finally, we get to sort of our tornado genesis time. And again, you can see that these parcel trajectories are, again, kind of maybe starting from the inflow, but going up and over the outflow boundary, descending, and then getting amplified by the updraft and then becoming a part of the tornado. So this is a different view of what's going on with that, and kind of following a single parcel trajectory. And then you can break up the vorticity budget components into their individual terms, just like with that Lemon and Doswell paper, where you had each term in its own little category, and you can track those over space and time and see what are the biggest contributors. And so this is just a different way of looking at things. And what you find is that the parcels, as they descend, so this is your altitude of the parcel, as it descends, you actually go from initially negative vorticity to neutral to positive, and then become part of the tornado. So there's some interesting physics that are happening there. Here you have your baroclinic term in here, which is going to be really, really small. I actually don't even think the blue arrows are visible. Yeah, you have a baroclinic term that's slightly visible here. Tilting and stretching is this green one. And so it's a useful way for diagnosing the individual contributing factors to tornadogenesis. And without getting into the super nitty-gritty of it, they basically found this baroclinic mechanism to be a really important way for getting horizontal vorticity generated within the storm and then reorienting it into the vertical. Sorry, let me catch up with my own notes here. So they found environments with large amounts of streamwise vorticity, so strong wind shear in the low levels that is aligned favorably with the storm motion. It results in stronger mesocyclones closer to the surface. So this idea that the stronger your mesocyclone is and the lower to the surface it is, the stronger that pressure perturbation gradient force upward is to lift parcels. But you can't have too cold of a cold pool, otherwise you can't lift those things. And so this is where it kind of becomes a Goldilocks problem of you need a strong updraft, but you need a downdraft with cold enough air that's not too cold. And so this balance between the two for a long time has been what people have been trying to understand for initial vertical vorticity within supercells and tornadogenesis. They found that weak negative buoyancy does not develop a strong enough near surface circulation. So even if you have a really strong updraft, there's some limit where if you don't have enough of a cold pool in these simulations, you just don't generate enough vertical vorticity. So hearing that it's an intermediate problem or a Goldilocks problem is usually when you just want to throw your hands up in the air, because when are we ever going to be able to measure some of these things precisely enough to predict them? And so that's one of the challenges. But there's some caveats with all of this. Many of these simulations have a sufficient resolution for resolving supercells, but not necessarily tornadoes. And so we call these things tornado-like, but they're not tornadoes. They miss key things like corner flow and radial convergence, and even just the resolution necessary to resolve the flow. Typically in modeling, you need 6 grid points across some feature to consider it resolved. At least that's like a good rule of thumb people follow. Another thing to keep in mind is that all those simulations we just discussed were free slips. So the impacts of friction are completely neglected, and tornadoes happen in a frictional turbulent boundary layer. So this says nothing about what's going on there. Roberts et al. 2016 and 17 sought to simulate and evaluate the role of friction in tornadogenesis, and they found it to be a leading cause, which was interesting. But what's even more interesting is a lot of those tornadoes in the simulations develop before the cold pools even generated. So what that says is that there's probably an over tuning or over reliance on frictionally generated vorticity in that simulation, and it's just kind of overriding everything else. Physical numerical chamber model studies show friction is important in generating the strong tornadic winds near the surface. So we know we need to account for friction, but it's been shown and through some other simulation studies that our current understanding of the surface layer and thunderstorm outflow is just severely lacking. And so standard boundary layer application of friction, something like a log law that you probably have heard about before, where the wind profile kind of goes to 0 near the surface, don't quite work. In fact, what do you like? Is the wind speed at the surface inside of a tornado 0? I don't think you can say that when you're lifting dirt off the ground. I don't like that's you got W is greater than 0 at like 1 micrometer above the surface. Like I don't think your log law is necessarily gonna work too well here. So we know it's a problem, but it's also a problem in the way we simulate it, because that log law stuff involves a lot of assumptions that don't work in thunderstorms and tornadoes. So you can't just apply friction to a simulation and call it good, because then you actually start over diffusing. Basically, it's I think from the study, it was 1,000% more non-dimensional shear if you turn on friction in these scenarios without the right configuration. So of course you're going to generate tornadoes very quickly if you have that kind of friction. But the problem is the true magnitude and role of friction in supercell tornadogenesis is still unknown and ongoing research topic, which leads me to a slide I literally added yesterday because I was made aware of a really great talk Paul Markowski did at NCAR. You can go to the NCAR YouTube channel and find this if you want to watch it yourself. It's really interesting, but he's been trying to tackle this problem of friction for a good while now. And he found some interesting stuff in some simulations where he found that the whole concept of the baroclinically generated vorticity might not even actually be the case anymore, because it turns out in those simulations, you don't have a frictional boundary layer, you're free slip, and you don't have any parameterized turbulence. And so what happens? Well, your primary source of vertical vorticity is going to come from reorienting baroclinic vorticity. What happens when you have a turbulent boundary layer with fully resolved eddies and friction? Well, you start to see that the vorticity sources do start coming from the inflow instead of the outflow in the cold pool. And so it kind of turns this whole problem on its head again. And we're going, okay, well, wait, now it's not the rear flank downdraft, and now it's not the cold pool. Now maybe it could be boundary layer eddies being ingested by the updraft. The answer is it's probably all the above. As you've kind of seen with some of the stuff with the Hodographs and the pressure perturbations, once you put a low pressure perturbation over any sort of source of vorticity, it's going to tilt, stretch, and amplify it. And so I think as a field, we're starting to kind of converge on this idea that really there are multiple ways of generating vertical vorticity. And what matters is how the low-level updraft interacts with it and enhances it. And what's going to drive the low-level updraft is going to largely come from the environmental streamwise vorticity, especially in the 0 to 1 kilometer and 0 to 500 meter layer for storm relative felicity. And so I just wanted to throw this in here as well, as basically to say that we're already kind of turning our own understanding on its head of where vertical vorticity in supercells comes from, and it's continuing to evolve, and it's probably going to continue to evolve even more when we throw in things like anvil shading from radiation, or we get better microphysics schemes, or we get better surface friction and turbulence closure schemes. I say all this to say that you're going to hear over your careers how new simulation studies show new things about tornadogenesis, and really this is the new mechanism, or that's the new mechanism. And it's going to continue to change, but really it still has to go back to the fundamentals of how do we forecast them, and how we forecast them is actually pretty well. So the physics still have to relate to what we know about forecasting tornadoes, but it's going to change in its actual application of what happens on the storm scale as we continue to get better simulations, as we continue to collect better data, and as we continue to increase the complexity of the variables, things like, again, radiation, anvil shading, stuff like that. So it's really exciting stuff, but it changes so frequently, it's really hard to keep up with. So go, if any of you are going into research, go make it even harder to understand, come up with some new stuff, turn our understanding on our heads and make us question our assumptions. So I haven't said anything about non-supercell tornadoes. So I figured I would throw in something in here of the one thing we haven't talked about, the aggregation of existing environmental vertical vorticity. Turns out that's a pretty good way to get land spout tornadoes and non-supercell tornadoes with non-rotating updrafts. So water spouts, land spouts, gust nados, that sort of thing. You can just aggregate your vertical vorticity from sitting on top of a boundary, slow moving cold front, slow moving outflow boundary. A lot of, I think some cold core days kind of can benefit from this as well, where you can get really strong lifting of vertical vorticity from existing boundaries from these very rapidly rotating mini supercells, as Cameron likes to say. And so I just wanted to throw that in there to kind of complete the picture of you can pretty much get a tornado from any source of vorticity as long as you have the right conditions with your updraft and storm. Where it gets really interesting is how do you get long-lived and violent tornadoes, and that's a whole different problem for a different presentation. So how do we use any of this simulation, pseudo understanding stuff to come up with forecasting for tornadoes? And you'll hear more about this from Rich, but we can relate these things in our simulations to the observables on the larger scale. And you can either thank or blame Rich for the fact that we get to work with this. I prefer to thank, but see what you guys think. But we use mixed layer CAPE to assess buoyancy of thunderstorm development. That one's a pretty much a no-brainer. But how do we assess things like, what our potential cold pool buoyancy is going to be, or evaporation potential from dry air entrainment and stuff like that? Well, I shouldn't say Rich found that the lifted condensation level is a pretty good proxy for some of these sorts of things. So lower LCLs are indicative of higher boundary layer relative humidity, which means less evaporation for hydrometeors, which probably means you're not going to have as strong of a cold pool. And so if you're relying on any vorticity in that cold pool, you're going to be able to tilt it and stretch it more readily than if it were, let's say, high LCLs. We have lots of evaporation potential, colder downdrafts, and harder to lift by those dynamic pressure perturbations. Mixed layer SIN is also included to spatially narrow STP. And then also just the caveat of mature supercells can persist into larger SIN. So this is actually something that catches people even in the weather service, is the idea that once you get a supercell going, it can persist into large SIN and relatively low CAPE for a very long time because of those updraft pressure perturbations. So that's just something to be aware of, that these parameters can't capture everything. The bulk wind difference and wind shear is used to discriminate between supercell storm mode. That should make sense after the Hodograph lecture you guys just heard. Storm relative helicity for the low level shear. Same caveats with the storm relative wind versus, or excuse me, a storm relative wind magnitude versus the streamwiseness of the vorticity. That issue with storm relative helicity still exists in this case as well. So you still have to interrogate your individual profiles and come to your own conclusions. You can't, again, fully composite everything all the time. And then recent work by Bryce Coffer suggests that the surface to 500 meters storm relative helicity may be an even better discriminator than what is currently used in STP. This was an old slide. I think, if I'm not mistaken, we're using surface to 500 for STP, just period, right?
There are a couple of versions.
Okay, so there's still a couple versions running around, but
calculated.
so that's just something to keep in mind, is that there's different versions of it and different use cases, and it might even change again as we're looking at things like with entrainment CAPE and how that might affect STP and how we can leverage that. Okay, so that was a lot of stuff to get to Vortex 2 ensemble environments. So in Vortex 2, they took a bunch of weather balloon profiles from tornadic and non-tornadic supercells, and I want to hear your thoughts about what are some of the key differences between these tornadic and non-tornadic profiles now that you guys are experts in SKUTs and Hodographs. So what are some of the primary differences you notice? Yeah.
Well, the tornadic photograph is more storm relative helicity. It appears that way with the loopy.
I mean, they're both pretty loopy. I'm bad at eyeballing, the magnitude. I would say they probably have roughly the same amount of helicity. So, but maybe I'd say maybe the bottom one has a little bit more. I wouldn't say that's wrong. I'm not quite sure I can objectively evaluate that. Yes.
The vorticity vector at the surface in tornadic photograph is a lot more streamwise than on the non-tornadic photograph.
Yep, absolutely. So you have more streamwise vorticity in the red hodograph than you do in the non-tornadic hodograph, and you can kind of see that in this kind of kink right here, where you have almost purely crosswise vorticity in this sense. So it's not ideal. Yes.
Another thing I see is on the non-tornadic QT, the what I'm assuming to be the dew point line is like just a hair drier there.
Yeah. So what would you say about your LCL heights between the two?
It's gonna be higher than non-tornadic environment.
Absolutely. And so what's that going to more than likely do to the cold pool temperatures?
It's gonna be a stronger cold pool and colder.
Yep. So harder to lift those parcels from the cold pool, tilt and stretch them into vertical vorticity, harder to generate tornado. Yeah.
So the non-tornadic load 500 meter and 1 kilometer relative winds are below 10 meters per second in the V. And for tornadic ones, they're above 10 meters per second.
Oh, so the basically the magnitudes of yeah, so more shear, more storm relative wind, yeah, so probably bigger updrafts and better inflow overall. So yeah, those are all. I don't think I noticed anything else terribly different. You guys already hit it, but is there anything else you guys noticed that maybe I didn't see you want to bring up?
This is another one to point out why it's important to look at the photograph. Look at the winds and near the surface in the non-tornadic. They're actually more back. Most people just, oh, well, they're more back. That's automatically better. No. What does the actual shear profile look like?
Yeah, and what does that do to your vorticity vectors? And
The only other thing I maybe notice is that the curvature in the low levels of the tornadic one, it's a bit more of a true concavity compared to the top one, so maybe a little bit of a boost for the right mover from that.
Yeah.
Heavier stuff, but that might be limited in space.
no, I think that's. I mean, you're the expert on that too. So,
Whole hand wavy sometimes.
but otherwise, I'd say they probably they have fairly similar lapse rates. They have roughly similar sin profiles, barring the lower dew point. You probably have a little bit more sin in the blue one. Yeah.
Yeah, so you also have in the tornadic case, some better venting of precipitation with stronger.
Ooh.
relative.
That's a good one. Yeah, there's a kink kind of in the upper level winds right about here. So maybe not as good precipitation venting in this case, which could cause maybe some issues with maybe like keeping your updraft steady state. Yeah.
I don't know how relevant this, but you have a higher shear magnitude from 1 kilometer to 3 kilometers in the non-tornadic. So maybe there can be some sort of trade-off between hail and tornado favorability though.
Yeah, possibly. I am not super well versed in hail. So Cameron, do you have any comment on that?
Yeah, I mean, it's a signal I've noticed with hail for sure. I think we need to understand more what the shear itself does.
So yeah, so this is just kind of meant to show you that these things actually show up in the aggregate sense when you start sampling storms. So it's not completely totally hand wavy, you know, like we're getting pretty close to the truth here, but there's even with that, there's still so much interstorm variability that even if you were given that tornadic hodograph, not every storm in that environment is going to produce a tornado. And that's where things start getting really frustrating too, is that you can have, you know, pretty much the perfect scenario and we still miss sometimes. And that's why it's important to keep collecting data and researching and running new simulations. So with that, I figured I would show a little bit. Oh yeah, go ahead.
I was just saying one thing, like this is a Parker 2014 study. They only had 14 photographs that actually compose 2 of these. And when you actually look at other observed photographs, you actually get differences between the non-tornadic and tornadic too. Like Mike Caniglio's study from a couple years
Yeah,
ago.
Mike's got a whole, he composited like
200.
everything that was available from the field projects and some of the differences in the storm relative flow are a little more pronounced
Okay.
than tornadic storm. It's actually a little more removed from the photograph than even what you see.
Is that related to the one where they were comparing the field project soundings to the RAP profiles as well?
It's kind of all
Okay.
intertwined. Yeah,
Okay,
there's a
because
couple other
I've read that one. I've not read the other one. So thank you guys. See, this is also helpful for me. I get to see what I've missed and
I think the coolest part of that paper too was like the shapes of the photographs were actually really similar, but like the storm motion relative to that photograph is different. So like those tornadic storms were moving in a way that did increase their outflow.
Yeah.
Yeah.
Which, yeah, if anyone wants a really good project to try and figure out, make an impact, come up with some cool storm motion estimates, or maybe even come up with something that accounts for the transition from mean wind to right mover or something like that. That would be a great area to improve upon what we have, because yeah, bunkers motion is not perfect. And so if you're again trying to forecast this, you have to come up with a reasonable estimate for your storm motion. Thankfully, in more of a mesoscale analyst scenario where you have storms ongoing, you can alleviate some of those problems. But that's a good area of research if anyone's looking for it. And so I just wanted to close out with kind of showing some of the stuff going on in the high resolution simulation world, and then also kind of tie in this idea that adding complexity kind of changes the answers we get to, and how, for example, including boundary layer turbulence to start showing interesting things. There we go. Is it gonna run? Okay, it's kind of running. It's chugging. It's chugging its way through. So simulations are cool in that we can come up with pretty accurate looking depictions of reality. But I show this to say that don't let the accuracy or the appearance of accuracy fool you into thinking it is reality. It is all too easy to get caught up into thinking that you must be getting close because that looks like a supercell. I mean, I've seen a few that look like that before, and it's producing something that looks like a tornado. And you've even got Mamadis in there. And I mean, it's not like you have a Mamadis parameterization scheme you turn on or anything like that. This is all just coming from the natural evolution and flow of the math of the fluid dynamics. And so it's exciting. It's exciting that we can now simulate a tornado with its parent supercell instead of breaking them up into individual chamber models or two cores for a single to resolve a tornado. But it's a little dangerous sometimes. But it really allows you to kind of peel back some of what's going on in full 3D flow. And so you can see the helical nature of a two-cell tornado vortex, and you can see horizontal vorticity being oriented into the vertical by the cold pool. You can see vortices along the leading edge of the forward flank downdraft being tilted and stretched and amplified as it's getting towards the updraft. So you can see a lot of very interesting things from these concepts we've already been talking about, but at a much finer resolution and kind of maybe at a more complete 3D flow view of it. But it's also really hard to untangle causality from a lot of this, and that's where researching this gets really tricky. So I wanted to show, I guess I'll preface with, for my thesis work, I did a similar simulation to what Lee Orff did. He's my advisor. But I did a fully turbulent boundary layer to kind of try and account for making sure we're fully resolving turbulence and getting that into the inflow. But it's still free slip. If you have questions about that, it's not technically fully free slip. It's this weird pseudo free slip that still produces diffusion near the surface layer. And for those of you that know what that means, we can talk about that later. But it's an interesting in between true free slip and this full friction that we know is a little too overly dissipative. And I just kind of tracked where vertical vortices associated with a pressure minimum at their center, kind of where they come from and evolve. So these colors of these blobs don't really matter. They're just like the ID of what object it is out of the total number of objects, and then just tracking them. And so you can kind of see that you get this aggregation of vertical vorticity along the interface between the inflow and outflow. Some of these come from the warm inflow and some of them come from the cold outflow. And all of them, I'm going to go back one more time, all of them end up at the same place, which is underneath the updraft. So this is kind of more of an in-between simulation to what Markowski's presentation on YouTube is talking about. His kind of shows up as being more impactful on the inflow side, whereas this one's more at the interface. And then if you do a free slip simulation, it's kind of more the cold pool side. Yes?
Is that a failed inclusion I just saw there?
Most likely, yeah. If I remember correctly, there's a failed attempt at tornado genesis the first time around, and then the second time around it comes around. You can also see the rear flank downdraft is kind of, I'm going to try to go back one more time, as these, so this is, I didn't mention, this is like a temperature perturbation or buoyancy perturbation. So these warmer colors are your rear flank downdraft because it's this dynamic downward force that warms as it's mixing, versus you see the forward flank downdraft is this cold downdraft due to the hydrometeor. So that's how you can tell the separation between the two. And then, yeah, the accumulation of these vortices. And so when you append all the tracks together, you can kind of get a neat idea of where all your vertical vorticity is coming from. So a little bit of here, a little bit of there, but really not a whole lot from back here in the rear flank downdraft, where a lot of time was spent thinking that that's where tornado genesis mattered. And it's not to say that it doesn't, but it's an interesting alternative to what was the norm for a while. And then you kind of see this, mix of cold trajectories, or I guess they're not really trajectories, but cold vortices and warm vortices on the inflow. And this white track is what eventually, or is the tornado track. This is all in a storm relative framework. So this is the tornado's movement in the storm relative frame, and it's all at one time step. But yeah, just to show you that the science is evolving and the resolution helps us, but you always have to check what your assumptions are going into it. And so in this case, there's still no friction, there's still no radiation, there's still no anvil shading. And so we don't know when we start turning on these other things in the real world, or even including terrain, how that's going to change our answers. So that's a tricky thing. I also want to throw this in here too, because I think it really sells home the point of how important the dynamic pressure perturbations are in lifting parcels from near the surface. And so these gray isosurfaces are your pressure perturbation, and these blue isosurfaces are your buoyancy perturbation. And so I think it's a -2 Kelvin surface, but you can see how it's lifting that cold air off the ground and up and into the updraft. And you can see how this lobe of low pressure is kind of correlated with where those vortices along the forward flank were being tilted and amplified. So there's this feedback process that happens between low-level updraft and low-level vorticity sources. And again, trying to drive home this point that I think if you stick enough horizontal or vertical vorticity underneath an updraft like this, you can probably get a tornado. And I think that also accounts for some of the randomness we see and why some storms do and some storms don't produce tornadoes. You're not going to be able to observe every eddy along the process. And some of that has to do with this feature identified in some of these simulations called the Streamwise vorticity current, and there's still ongoing research on how that may or may not play into tornadoes. It seems to be something that's not required for tornadoes to happen, and just because you have a Streamwise vorticity current, it doesn't mean that you will have a tornado. But a colleague of mine is doing some really great work going out in the field and measuring these, and if you're interested, I recommend checking out Sheath et al. 2021, and they went out with Ka band radars and started sampling with RHIs this region of the storm to try and better sample and better collect data on where some of these vortices are coming from and where this low level updraft interaction with these vortices are coming from. And so I just wanted to throw that out there in this kind of feedback process of forecasting, theory, simulations, data collection, and then we go back and we do it all over again. And so now that they're out collecting data, eventually there'll be enough data collected to go, hey, we need to try something with this. And then we'll go back to simulating again, which will then result in another forecasting technique and so on and so forth. And so with that, I will leave this up here and take any more questions you might have. And then if not, I'll leave it up to Rich.
Okay, now let's try again. Okay, I appreciate everybody staying this late. If just so y'all don't feel bad, I got up at 6:30 and I've been here all day. So we're gonna try to tie this stuff together, and Kelton kind of went over this, and I want to break it down into 3 basic convective modes to talk about tornado forecasting. But first, there is an extremely important public service announcement, and I want y'all to take this to heart. I'm not going to say it's just flour. I mean, what are you talking Okay. Okay, y'all are awake now. So okay, we'll deal with the serious part here. Point is, if you're gonna be good at this in a forecast sense, it's not as simple as some 2-second shortcut. It's not that information isn't valuable. You're going to have to think about it. Okay, non-mesocyclonic tornadoes or land spouts, water spouts, you frequently see these in clusters strung out along boundaries. I'm not going to spend a whole lot of the mechanism is you've got a swirl on a pre-existing boundary. If an updraft sits over that, you can amplify it to a tornado. It's pretty straightforward. You don't need any of the other fancy mechanisms.
So they're simple and difficult to forecast. The hard part is finding the right synoptic or mesoscale boundary that has the vertical vorticity and is sitting there with storm residence times long enough. If you can get sufficient buoyancy, not too much inhibition, and you got good low level lapse rates, good stretching profiles thermodynamically, you can get these. Key is you have to look at, do the storm stay on the boundary? And if you can get all that to line up, a tornado is easy. An updraft and a swirly. How many surface-based thunderstorms does the US get a year? A million? I don't know. So there's a lot of storms. So clearly it's not that easy. But when you look at it, every once in a while you see one of these things along the Gulf Coast, and you're like, you know, what the heck was there a tornado with that for? Think back to this. And again, once you start getting cold outflow, that tends to short circuit the process. So I'll show a real world example. No more model simulations or anything else, even though this is a pseudo model analysis. This is a case back several years ago. I've demarcated a stalled boundary. It's a slow moving cold front across Kansas. So we'll focus on the roughly northwest Oklahoma, Kansas area. How would you characterize the moisture in the warm sector of this scenario? This is a mid to late May case. So those are 56 to 60-ish dew points in the cyan and green. Is that good? No.
Not optimal at that time.
So suboptimal, and now you're thinking in terms of supercells and tornadoes, kind of suboptimal. But we do have, clearly it's colder to the northwest, right on the leading edge of the temperature gradient is where we mark the front. And there's a dry line feature in western Oklahoma. Okay, so the buoyancy field. Now, what is different about a case like this? What do you think looks odd where I have the surface wind shift? What about the buoyancy field is different than, say, a typical March cold front? You've got buoyancy on both sides of the boundary, which is actually not terribly common. And this case is nice because it's strongly capped out in the rest of the warm sector. So the only place you're going to get storm development is in the narrow zone along the Bear Clinic zone. LCL heights. We talk about high and low, and of course we help you with the color coding. Look along that segment of the boundary into South Central Kansas. Are those particular, what you would call favorable LCL heights?
No,
For
exactly.
tornadic supercells, that's over 2 kilometers. So these are big temperature dew point spreads, 30 degrees and larger, fairly high cloud bases. So, okay, so we're starting to look like kind of a marginal scenario for supercells, steep low-level lapse rates. And notice it's not just on the warm side of the boundary, it's centered on the wind shift. Deep layer vertical shear, this is just one measure. This is just the bulk shear, 0 to 6 kilometers. Strongest where the flow is northerly on the cool side of the boundary. Marginally favorable on the warm side. So it's kind of a low end supercell type environment. Low level shear, is that impressive by any means? No. This is so it's a weak low level shear, modest deep layer shear, moderately unstable, kind of high cloud based environment. Not something that's just going to jump out and say, hey, there's going to be a ton of tornadoes today. This is convergence and vertical vorticity along the boundary. So the red contours are the convergence scale to this type of analysis, and the vertical vorticity is shaded. So there's a lot of swirl or potential spin already oriented in the vertical along this zone. So you combine steep lapse rates, moderately large buoyancy. And the question is, if you can get updrafts to stay in this zone, what might happen? Because is the vorticity is it on this scale in reality? This is a 40 by 40 kilometer analysis. No, that frontal zone collapses down much smaller. So the vorticity is concentrated on a much smaller scale than this, but this is the observable scale. All right, so we get, this kind of looks like the example Cameron showed with the supercells zippering back down southwest down the boundary. But notice right through here, these are mature storms. You just barely get, now this is the lowest cut, so a log. You see outflow, this little fine line. This is from the mature storms farther northeast, and where that's intersecting and ahead of that, you're getting new development along the front. And so you can see over time, new updrafts are developing southwestward. Doesn't look supercellular. It looks just more like there's just general convection. However, there's a cyclonic shear zone
all through here, and notice there are periodically little swirlies on this, and this is from Vance or from Wichita. You amplify some of these. So as these new updrafts form and it's close to this intersection, which what would the intersection of this outflow and the front tell you about the low level lift? It's going to be stronger. There's more mass convergence there. So you get the swirlies to get into that zone of the strongest lift, new updraft development.
And maybe more vorticity.
And perhaps more vorticity even on scales that are going to be hard to observe. And these kind of things happen. And you get sequences of tornadoes that develop southwestward with new convection along the front. And a couple of these produce the F2 damage. So they're not always of no consequence. And again, you can look at the cloud base and things. Does that have all the characteristics of a classic tornadic supercell? I mean, there were arguments in real time about if it was some kind of hybrid, but the whole notion is you've got this whole area of severe weather and there's only a small area where the tornadoes occur. So these are hard to forecast, but if you're looking for them, you can find them. All right, limiting factors, as I said, low level static stability is the enemy of tornadoes on all scales. In this case, when you get too much cold outflow production, because you notice where the outflow was up to the northeast, that's not where the tornadoes were. That's where the mature convection was. It's with the new updrafts. And in this case, the storm stayed close. The front and the storm motion matched enough that the updraft stayed in that zone of vertical vorticity. These are going to be difficult to forecast very far in advance. Have any of you noticed an event like this? I mean, in my experience, once every 1 to 3 or 4 years, if there's a favorite state for it, it's probably Kansas, maybe Eastern Colorado, but you know, you can go several years without seeing one. If you want to try to look for this stuff in real time, we do have some stuff on the mesoanalysis page. This is some people call it the cheat code. I won't say anything more about that, but the idea is you've got low level cape and vertical vorticity combined. This just says something about, is there a swirl? Is there the potential to amplify it? And then you can also, there's a non-supercell tornado parameter. This one, if the shear is too strong, you won't see anything. So if the deep layer shear, so it will actually zero it out, because the problem is storm motion tends to be too fast and it won't stay on a boundary. Okay. Any questions about landspouts? Good. I wasn't going to answer them anyway. Okay, we'll talk about tornadic supercells. We'll test the weenies. What storm is that? 5, 4, 3, 2, 1. What was it? Good. Yeah, it was the cold storm. Okay, supercells are fairly predictable. That's nice as a forecaster. It's not like some mystery we're sitting around like, wow, I thought there was going to be stratiform rain today and there was a 70,000 foot top supercell. Had no idea. It's not that bad.
It's like it was today that like you weren't sure the cap was going to break.
Yeah, now, yes, there are days where you're not sure you're going to get storms at all. That's very much, convective initiation is still a very real problem. But if you can get semi-discrete updrafts in an environment with substantial buoyancy and vertical shear, the right Hodograph shapes, all that stuff, you can get supercells. And of course, the rotating updraft is stronger, especially below the level of maximum rotation. That's the pressure perturbation argument. It's the vacuum cleaner. So you end up with a stronger updraft lower in the storm than you would get from buoyancy alone. And of course, the importance of that is you can force air up, and this is how the storm continuously regenerates itself. And of course, another side note is rotating updrafts are less prone to dry air entrainment, and they're more resistant to decay. So these things can hang on a lot longer than you might think, and you get a stronger, longer lived storm. All right. So what do they look like on radar? This is the El Reno storm, just to show you that there are direct observations. Even you don't need a Dow radar. You can see this with the 88D. Here's the early indications. This is only at like 3,000 feet. So this is pretty low, but you see this area of up to about 65 knot storm inflow. This is for an east-southeast storm motion. And you see what happens. Look at this. It's only like 15, 20 minutes. The inflow increases from 65 to the low 80 knots in the storm relative sense. So it's a like 25–30% increase in the strength of the storm inflow over like 15 or 20 minutes. Now, this is the early stages of the El Reno tornado starting, but you should be able to see this aloft too. So this is looking at 20,000 feet above the ground. You see broader scale rotation, moderately strong. And then 20 minutes later, not only this is the evidence of the developing tornado, but look how strong the broader rotation is in the storm. That's a 70+ knot V-rod at 20,000 feet. This is the vacuum cleaner. Now, can you say, without any doubt which led to the other? It's not necessarily cause and effect, but you can say that they are clearly related to one another. So you see this in the real world. You see that big increase in the storm inflow, especially before serious tornadoes. You see this all the time. All right. And then what does that do? Here's looking at the precipitation aloft. So you've got initial precip formation. What's this feature? What's that weakness? Again, this is at about 20,000 feet. A bounded weak echo region. This is a sign of an intense updraft. So the updraft is stronger. The mass response, the mass flux through the updraft, everything, it's all consistent. And then what does this do? These are all time matched. So these are the low level scans. What does a rotating updraft do to the precip distribution? You get the standard supercell and HOOT configuration. And this is all right up to about the time the tornado formed. Okay, this is just a picture. You've seen several of them. But where is the forced descent in that picture? How high? I'll just start the cursor. Is it forced descent up here? Forced descent? Forced descent?
There.
Okay, somewhere down here, forced descent. It could be forced descent all the way down. That laminar structure, that is something where the storm itself is drawing air in and up. That is air that is not buoyant at that level. So it's a direct reflection that there's some convective inhibition in the environment and there's some forced descent on the storm scale. All right, so what do we think we know? We've talked about this off and on for 2 hours now. Downdrafts, the thought was they're critical for near surface vorticity generation. It's either baroclinic generation, it's just frontogenesis, right-hand rule, same thing applies. Or where you can use that and figure out the orientation of the vorticity vector and you reorient it. And if it's too cold and too stable, it doesn't matter. Think of it as like molasses. If you have swirling molasses, it doesn't matter. It's swirl that you can amplify. Okay, that's fine. This is the old Markowski, Richardson et al., their whole version of it. Is your reorienting vorticity along the forward flank? Again, with baroclinic generation, it's a little bit more complex looking than that shows. But the point is, if it's not too cold, it's not too stable, you can amplify this into a tornado. Okay, that's been the primary school of thought for the last decade. And then again, you can amplify this stuff. Now, real world observations kind of bear this out. On the top, these are, well sampled storms compared to what you're going to see day to day. Those are temperature or buoyancy perturbations. The darker blues would be more negative, more stable. Lighter colors or pinks would be positive perturbations. So the tornadic storms on the top, you notice the air in the vicinity of the hook echo. First of all, the hook is narrow. So what does that tell you about downdraft and rain cool production from that precipitation? A lot or just a little? What about the bottom ones? These are the same reflectivity contours. So it's a lot more, a lot thicker, broader hook echoes and much more negative low-level buoyancy perturbations. So the idea is the bottom one is it's swirling, but it's cold molasses. It's hard to lift that and do anything with it. Okay, so it's been mentioned here. There's more recent work that says not so fast. Maybe it's not quite as easy, but there's some aspects of this that aren't too scary either. Maybe the vorticity isn't that we're talking about what is initiating tornadogenesis. It might actually be coming from the warm side. In reality, there might be a whole spectrum of processes at work. Some of them dominate in particular environments on one day and other processes dominate other ones. I don't pretend to know. And it really gets down to where it's something akin and smaller scale than horizontal rolls, not like you've seen like cloud streets, a horizontal convective roll. This is something smaller scale and closer to the ground than that. But what's neat about this, if you're getting vorticity, shear related vorticity, low level environmental shear in the inflow side of the storm still matters because that's what's generating the vorticity. Resistance to displacement still matters. If there's a lot of inhibition or high cloud base and there's any preset generation around, that potentially mucks it up. Now, can anyone think of a problem with just using the LCL height? Does that explain all the variability in downdrafts? What are other factors that you don't get from, you just look at the LCL. What are other things you might want to consider?
Dry air a lot.
Well, potentially, yeah, because a deeper source for a downdraft. What else? Exactly. Do scattered large dry hailstones produce the same evaporation as lots of melting little wet hailstones? No. Small raindrops versus large raindrops. You can get some of that from dual pole data, but so it gets pretty complicated pretty quickly. And I don't honestly know how to tell you how to say, here's what the hydrometeor distribution is going to look like in the Hook Echo 6 hours in advance. Good luck. Okay, so if the whole point here is that every time I give a presentation like this, I like to try to frame it in the same way because Kelton mentioned it, and is that if anything you come up with, and some of you are could end up working on something that helps to refine our understanding of some part of tornado genesis. If it looks to be completely at odds with everything we've done to this point, that's cool to say, wow, I've turned everything upside down. There's a pretty good chance you're full of crap too, because why does the stuff work? You have to consider it's not just, did I do it? None of this stuff where we say, Kelton earlier gave me credit for something. It's not just me. There's decades of stuff, and it's just a little piece of the puzzle. Point here is think about it in the general sense. What's the importance of a right moving supercell for tornado genesis? What do you think the most important thing? There's two aspects of a right moving supercell that are critically important to tornado genesis. What are they? Okay, you're sort of dancing around it. What are things that represent? What are if you want tornadoes, I'll give you a hint, window of opportunity.
Just more inflow, right? Or like in terms of like more like in terms of like into the storm.
Well, there could be more mass. I mean, it could be larger storm. Maybe that's related to a larger tornado. I don't know.
What was the key aspect of that story time? That we
Think back. What makes a supercell unique compared to other storms? Yeah.
I was thinking low level instability and what I think the pressure.
Okay, so it could be okay. Now we're starting to get the pressure perturbation. What does that do to the low level updraft?
It strengthens it.
Strengthens it. What does that do to the stretching term? It increases it. So any vorticity, whether the storm generates it or not, can be amplified more dramatically. And if you think it doesn't matter, how many of you have chased and seen the process with your own eyeballs? Good. I'm glad. If none of y'all raise your hand, I was going to leave. But it's like, what are you doing, Norman? So, okay, so it's you basically, and Kelton tried to emphasize this. An intense updraft close to the ground is 90% the way to getting a tornado. I mean, I'm just pulling that. What do they say? 60% of statistics are made up on the spot. And I'm making that one up. But the whole point is a strong low level updraft is one of the key ingredients. Because how else do you get that? The only other way you can do it is through the perfect thermodynamic profile with no disruption from anything else. Some of the land spout environments look like that for a short period. That hints at what's the other part that's important about the supercell. So it can help generate its own intense low level updraft and stretching term. What else is important about it? And hint, window of opportunity. Longevity. The more chances you have for a little more duration, the better the odds that it's going to work out something like the picture there. Okay, so if there's substantial near ground streamwise vorticity in the inflow, so if not just have a supercell, but is it rotating very strongly close to the ground? So that vacuum effect is as strong as possible. And do thermodynamic profiles help or hurt? If it's completely uncapped, like it's a moist, absolutely unstable layer for your inflow, is it going to be easy to, first of all, that's not very realistic. And can you maintain a discrete mode very easily? Probably not. It turns into a mess. But if there's 400 SIN and an LFC at 15,000 feet, that might be hard for the storm to replicate itself. Point is, and this would be my takeaway in terms as a tornado forecaster, is that all of these factors, you're looking for strong lullable mesos, strong stretching, and a greater probability. I should probably have that jump out the screen. This is not a yes, no thing. They're in a, what would be the fancy word, stochastic or something, where you've got, essentially there's a randomness to this. You're increasing your odds. That's what we're trying to do at SPC. We're trying to increase, say, hey, it leans more in favor, closer to yes, closer to no, but it's never either one of them. Okay, so the parameter stuff, I just want to make sure y'all understand where this comes from, because I know you can call this up and look at it on various model forecasts. First question, does the model influence the calculation? I'm not talking about the formula for it, but does the output of the model influence what's calculated? Yes, absolutely. So picking soundings in a simulated storm and then using that to forecast said simulated storm is circular reasoning. Like you're thinking, oh, look at this. I've got a helicity blob with what looks like an updraft or a reflectivity max. Now I'm going to pick a sounding right in. That's the equivalent of launching a sounding in the inflow region of an existing supercell. And then saying, wow, look at the SRH. Look at the moisture. Look at all this stuff. That is the supercell. You can't use that to forecast it. Okay. So I'll go through this fairly quick because it's already been mentioned. I'm not really saying anything new. We've got to consider the energy source for the storm. We've got to consider what depth. They were talking about early on, Harry and Cameron were what depth are we looking at? I'll show you where that came from. And then we've got to have enough vorticity to tilt and stretch to get a rotating updraft. That's the lullable shear. And we got to get the precip away from the updraft. That's kind of the deep shear storm longevity. But the question is, you can say deep layer shear, what do we mean? And this is just based on observational evidence. You got to go high enough to consider where the precip's forming, because that's from there up is where it'll be redistributed. And you've got to consider some of the limitations. So if you go back, this is like Weissman and Klimt, early 80s, which none of you are alive. I'm hoping not. You're not still in school. That would, because then you're damn near as old as me. And if you're still in school, if you came back, great. But if you're still in school, actually, I want to talk to you about how you got your funding. That was okay. So early models, were these models sophisticated by current standards? Or in terms of resolution, does, you know, like grid spacing and those kind of things, time steps? No. If they didn't have enough, if there wasn't a sufficient vertical shear through at least about 6 kilometers, the storm, these early models didn't even produce anything that resembled a supercell. So that's kind of where the 0 to 6 shear first came from, was not observational, but it was from the early simulations. So the question is, how do we account for the storm depth? We kind of loosely call it effective bulk shear. Shear is technically, you got to account for over the distant, the vertical depth. It's really the effective bulk wind difference. It's a bulk shear term. So we're just looking at the cape and the layer, the cape bearing layer in the sounding, and what part of the storm is contributing to the storm inflow. And then just break it up into layers, look at it percentage wise, and then figure out over what depth matters. So who's familiar with box and whisker plot? You've seen those. You know, it just shows the meat of the distributions of the box, and the whiskers can extend to some version of the extremes. If you envision this red line is the bottom whisker for the bulk wind difference. from the surface up, successively deeper layers over hundreds and hundreds of observed supercells. The blue one is the top whisker for non-supercell storms. So what would suggest the greatest separation in the distributions? If the blue line is below or above the red line. Remember, the blue line is the bottom, that's the top whisker, in this case, the 90th percentile. So if the 90th percentile and the red is the 10th percentile, where do you want the blue line to be relative to the red line? If at all possible. Below it. Where is it closest to being below it? Okay, so what's a standard EL height for typical central US supercell environment? 10, any other guesses? 10's not bad. 12 is very close. What is 50% of surface to 12? 6 kilometers. Imagine that. So it turns out if you scale to the depth of the storm, about the lowest half is where the best discrimination occurs. So the standard environment, that's 0 to 6 kilometers. If you happen to have a really tall storm, like a Gerald environment from the late 90s, the equilibrium level that day was like 18 kilometers. 0 to 6 is only the lowest third of that. If you actually go up to the lowest half, you have to look almost 0 to 7, like 0 to 8 shear, 0 to 8.5. It's in the supercell range. So just want to show what this looks like on a sounding. So this goes the effective inflow layer. We'll talk about that in a minute. You go from the base up to the equilibrium level for the most unstable parcel. That's your convective depth, is the white bar in the vertical. Halfway up, you're taking the bulk wind difference from there to there. That's the effective bulk wind difference. And this is where it comes from. So it's based on observational evidence, but it has theoretical underpinnings. So now the effective bulk wind difference, again, you can use it. The good thing about it is you can use it in a wide range of cases. That's why we put it together that way. What's the problem with 0 to 6 shear in a warm advection regime with elevated storms? Are you going to over or underestimate supercell potential? Under? Over. You may be including a lot of shear that's in the cold low levels, which is very common to have in those profiles on the north of a warm front type thing. So if you use the fixed layer 0 to 6 shear, you're going to get a different answer than if you use something that scales to the convective depth. And think about what we're doing at SPC. Is it easier for me to change parameters midstream? And well, it's almost like you have to assume the answer before you know which thing you're supposed to look at. This is meant to kind of dampen that out. So you don't have to, it's not like you're reaching in your toolbox and grabbing a slightly different pair of pliers every time. It's one that applies over a wider range of environments, tall storms, short storms, elevated storms. It kind of works the same. Now, just to show that it indeed works, this is the sample. This is the standard 20 meter or 40 knots of shear roughly. These are all supercells on the left, various flavors. These are storms that are clearly elevated, tornadic, non-tornadic. Down here in the bottom right, these are just run-of-the-mill, disorganized, according to radar, storms with no persistent rotation or structure. The transition is roughly, and these are ones that are the pseudocells, as I've always called them. It's like, well, it depends on how you squint and look at it. Is it a supercell? It rotates a little bit, or it didn't last very long. They're right there in the transition. So 15 to 20 meters per second is 30 to 40 knots. That fits with the earlier suggestion that somewhere in that 30 to 40 knot range. If you get higher than that, you're clearly in the supercell range. If you go clearly below 30, you're into some sort of non-supercellular storm mode. All right, low level shear. What do we mean? We've already talked about it. It doesn't matter if it's not part of the storm inflow. So this is where the effective inflow layer concept comes from. And all we're doing is applying cape and sin constraints, and I'll illustrate it for you. Now think about this for a minute. All the lifted parcel has to have is 100 cape. Is that a lot? No. 250 sen, is that a little? That's actually a lot. Are these what you would call a harsh constraint or a pretty easy to meet constraint? Pretty easy. So this is not something that's like, oh, it's unbelievable how hard it is to be part of an effective inflow layer. Does the lifted parcel have a pulse? That's really all this is saying. Okay, so what does it look like in a real sounding? This one, the inhibition part isn't really relevant, but if you just start lifting parcels, this is the layer that's highlighted, the contiguous layer of parcels that meet the conditions. So we start down at the bottom. Any buoyancy for this one? That's intercept, and I'm jumping every like 50 or 100 millibars. Does that one, can you see how that would meet the constraints? So there's a little bit of buoyancy. We move up, that's near the max buoyancy. So it looks like clearly there's very little inhibition. There's at least modest cape. You keep going up. What happens is we keep going up, the moist layer drops off and the buoyancy diminishes. So hopefully you can see from that illustration what the effective inflow layer is. So you're just doing that on every sounding. You're starting looking for cape and then working your way upward. And this is what it would look like in terms of illustrating the inflow layer on a hodograph where, and this is just like the example they showed. However many hours ago that was, I don't know. Where in effect, you can lop off this lower part of the hodograph is irrelevant for like an SRH calculation. So, and that's where effective SRH comes from. It's the SRH within the effective inflow layer using the bunker storm motion estimate. Now remember, there's caveats to all this stuff. There are potential errors at every step along the way, but in bulk, they work out pretty well. Okay, so just to show there was some other independent work. I didn't have anything to do with this. It was, gave them some soundings, but Chris Nowatarski down at Texas A&M and some others looked at the inflow layer. I was a little nervous when they started this because they could blow it out of the water. And it turns out that in the higher end supercell environments, it's a really accurate depiction of the storm inflow layer. I think they said 95% of the air involved in the mid-level updraft of these supercells was confined to the effective inflow layer. So now what kind of storms does it not work as well with? Maybe, but disorganized storms, because they don't have the pressure perturbation. They don't draw the air in. So you don't have the vacuum cleaner effect. So some of that, like at the top or the very bottom of the inflow layer, some of that's dependent on forced descent to get it going. And so in general, weaker storms really actually make use of less of that layer is one way to look at it. Now, this is where I mentioned like the playing with your soundings, the things like the Betz-Miller-Yannick scheme and the NAM can tremendously influence the moisture profiles. If you get in close where it triggers. Has anyone seen one of these? You've got effective SRH of 1,000, but then you look at it and the inflow layer is literally 6 kilometers deep. How many real world storms have 6 kilometer deep inflow layers?
0.
Not many that I'm aware of. So when you see that stuff, that's the fodder for weather Twitter. You notice you'll never see me on there commenting on this because I die before I actually respond to all these stupid things. But the point is, just think you're meteorologists or you want to be a meteorologist. You're on your way. You have to consider that kind of stuff. And again, that can blow the effective SRH out of the water because it's integrating way too deep. And then you look at some of those wind profiles, they're literally in the modeled storm and it's this perfect 70 knot half circle. Of course, the SRH is massive. And they're going, oh, well, we're going to have violent tornadoes today. It's not what we would at all call a proximity sound. Okay. Last, but we'll just go through these fairly quick. So I just want to make sure that you understand what goes into these, how they were developed. Supercell composite uses the most unstable cape because there can be elevated storms. So we can't limit it just to surface-based instability. We've got the effective bulk wind difference, 20 meters per second or 40 knots should look somewhat familiar. If the shear gets weaker, it starts to penalize it. And if it gets stronger, you don't get more credit. There's some other factors in here. And effective SRH, you don't need that much to get weakly rotating updrafts. And then also more recent work some other folks did. If you include the convective inhibition, that actually narrows the spatial false alarm on a parameter, especially when you're plotting it over a broad domain. So it reflects the ability of the storm to, you know, essentially the vacuum cleaner. How can it continually regenerate itself? All right, so just keep in mind this stuff. These are, where did these numbers come from? I just woke up one day and I just decided that sounds good. Driving to work and I'll divide by 1,000, why not? Where do they come from? Exactly. Now, do you know empirical studies of what? What kind of storms? I purposely only picked storms from southern Argentina, Western France. What storms would this represent? What climatology of in storm environments do you think this represents? The United States, the CONUS. Now, where are there more supercells than anywhere else? The Great Plains. So this is skewed toward the Great Plains. Now, so you'll have people say, well, you know, you need to change this, you know, if I'm going to use it in New England, because the climate of this entire sample of thousands of storms doesn't look like New England's supercell climatology. You could change these normalization terms. You know, in most cases, you normalize by smaller values to bump the composite up. But then what does that do in Oklahoma, where the storms are common? It blows the roof off of it. So you do have to consider regional climatology. What went into the development of the sample? This is CONUS-based. If your distribution doesn't look like the CONUS-based, then be careful with how you apply it. Sigtor parameter, it's the same thing. Build off of the supercell composite, except we'll focus more on low-level shear because that corresponds pretty directly with the strength of the low-level updraft. And can you amplify vertical vorticity wherever the heck it comes from? So the idea is looking for vorticity in the lower part of the effective storm inflow layer, and then considering both the LCL height and inhibition, because you notice the supercell composite didn't say anything about LCL height. Doesn't care. A high-based supercell doesn't make it a weak supercell, just makes it high-based. That doesn't necessarily affect hail production too much. So strong tornadoes are more probable when you get the strong low-level updraft and not much resistance to forced descent. Now, I will say that a lot of this stuff, you know, on the storm scale, Kelvin talked about it, you can't measure most of this, and we're nowhere close to being able to measure most of it. So there's not really a yes or no answer when it comes to applying these things. And I think you'll do yourself a great service. And I would encourage all of you, if you go out and chase, be honest with yourself when you go out as to what you expect to see and compare it to what you actually see, and then come back, and it doesn't stop there. Talk with your classmates, whatever. What the heck was that? Why did this storm behave that way when I thought this is what the environment was going to look like? I thought this is what the Hodograph shape suggested it should be. If you want to get really good at this, that's what you're going to have to do. All right, so effective layer STP, same kind of thing. It's just now we're focusing on terms that are skewed toward the empirical climatologies of tornadic supercells for the CONUS. So we've just added the SIN term is a little more important. LCL's new, lower level SRH. So which of these, there's two terms in here that primarily drive the numbers up. Which two are they? What gives you big STP? SRH, that's one. What's the other one that primarily drives it up? Well, think about the ranges of possible values. And I'll give you a hint. This one has sort of a cap, so it's kind of limited in what it can do. LCL changes it dramatically, but does it make it go up? It's a CAPE term. So CAPE and SRH, the two basic building blocks of supercells, are what drive this up. The SIN term is neutral. It can only decrease it. LCL can only decrease it. So they're limiting factors. Yeah.
Something I think could be added to a parameter like this to better represent would be low level instability, like if you go to 1 or if you go to 3 kilometers deep.
It has been considered. Statistically speaking, it hasn't helped in the versions that I've done. I've looked at low 0 to 3 Cape, things like that, low level lapse rate. To me, the improvement wasn't worth the complication. That was just my interpretation. Now, that's not to say that it can't be formulated in a way where that would matter. Now, again, would you trust this formulation as much in a high shear, low Cape environment? No. There's other things Kelton and I are looking at, like the entrainment Cape, which is not what the E here just stands for effective layer, as all that one is, that potentially our standard buoyancy calculation might be underestimating the effective buoyancy in these low shear or high shear, low Cape environments, and they might be overestimating the influence in like the summer Iowa cornfield stuff with supposed 10,000 Cape or whatever. So the point is, understand what goes into it and you can predict why it goes by. So when it goes haywire on a model forecast, a lot of times it's because of this term. The inflow layer becomes idiotically deep and it's not realistic. Okay, so just to show some of the other stuff, the STP, look at the key is to highlight the bottom table. If you just do a yes/no decision thing, kind of a simple 2x2 matrix, if you use STP versus other flavors of it, you get more correct answers and fewer incorrects, focusing on shear even lower in the profile. So it's a modest improvement statistically. Okay, now we do have fixed layer. You might wonder, why do you have all these damn versions of STP? What are potential pitfalls with the fancy pants effective inflow layer stuff? What does a model profile have to get right that's critical for that whole thing? What's one of the, I mean, it has to get everything right, but what is a non-conserved quantity that it has to get right? I mean, potential temperature and things, okay, there's some limits on what it can do. Are there limits on the mixing ratio other than saturation? Is there anything that says what the mixing ratio has to be? No. So do we have perfect moisture observations all over the place? We have surface obs that are pretty good. The mesonet, it's real good here in Oklahoma, but think on the scale of supercell, that would be one observation per storm. Like one single observation representing the entire storm environment. Probably not sufficient. So the point here is that if you don't get the moisture profile right, the whole thing can go out the window. So the point is, if you have a backup, and that's where we use surface-based Cape, because our objective analysis scheme also forces the RAP forecast. This is kind of how our mesoanalysis works toward the observations. It's got a short-term forecast of what it's supposed to look like, but we force it toward the observations. So if we use fixed layer and surface-based versions of all this, it should tell you generally the same thing. And would you be concerned if there's effective layer STP is 10 and fixed layer is 0.5? Same place. Probably a good idea to look at, what do these profiles look like? How can I get such a big difference? If they're similar, it just probably means you're not in a sensitive environment. So that's the only reason we do all that. And then fixed layer, same stuff, just surface-based versions and fixed layers for the shear instead of the fancy floating layers. It's just, we go with the standard ones. Okay, so weaknesses, you have to get a supercell. This doesn't explicitly tell you that you're going to initiate a supercell thunderstorm. There's all kinds of things. Is initiation the same as decay? Absolutely not when you're involving a rotating updraft. So it doesn't tell you anything about, so you're trying to get it to work in both scenarios that are extremely complicated. And, you know, those are different problems. LCL height, it's a miracle that it says anything useful about outflow character on the storm scale, but it doesn't tell you everything you need to know. And the stuff within the storm and looking at the vertical pressure perturbations and buoyancy variations within different parts of the storm, forward flank, good luck. in real time, figuring out what that's gonna look like. So you're gonna have to consider stuff. So, okay, is y'all okay if I still go? We're almost done. Okay, good. It's kind of like, it's their fault. So, because I'm not gonna go an hour. Okay, so convective mode, it's been mentioned multiple times. I'm gonna give you the crash course in convective mode in 2 slides. You'll be an expert. It's, and forget all the text. So we'll just do the 2 slides. Here is the prototypical recipe for semi-discrete convection. The things that matter that this doesn't explicitly say is the strength of ascent, but I'll pose a question to you. Do you think vertical motion on a standard dry line is stronger or weaker than vertical motion with a strong baroclinic zone? It's weaker. So what does that tell you about how many updrafts should you expect to initiate on a cold front versus a dry line? More on the cold front. So it's a little harder, plus the environments of dry lines. You have elevated mixed layers, maybe a higher level of free convection and so forth. But what gives you a north-south dry line is also a north-south lead trough because of flow over north-south mountains. It's the westerly component of the flow loft that sets everything in motion. That also gives you shear vectors and things and flow oriented across the boundary. What does that say about potential storm interactions? It's more limited. Now, what if this is a straight hodograph environment? Are the storm interactions necessarily limited if you have a very straight hodograph? Splits can actually run into each other. So where would you be looking for more discrete storms if you have a bunch of splitting storms on a dry line?
Initially.
Well, is it the initial ones? Or I'm saying, let's say that there are storms starting from I-40 up to I-70. What are the 2 places that you would typically look? All else being equal, if you have a bunch of splits and collisions, I-70 and I-40. Now, there may be other differences in the environment and your expectation. The other thing that I don't think people think about as much is that the way I've drawn this, our storm motion estimate is in the yellow. The boundary is moving slower. So the storms move out of the zone of ascent. You don't tend to accumulate new updrafts in the same zone. So does this make sense? And then the venting aloft, the storm relative flow, again, it's orthogonal or a large angle to the boundary. It doesn't have to be orthogonal, but it's just not parallel. So does that make sense? Your venting storms are venting away from one another or kind of parallel to one another. They're moving out of the zone of ascent and the zone of ascent isn't excessively strong. That's a recipe to keep storms discrete. And that's good for tornado events if everything else is favorable in the warm sector. Cold front, and some of this goes back to the thermal wind even. Boundary in this case, remember the motion is going to be orthogonal to the orientation of the boundary. So this case, it's a southeast moving cold front. Notice because it's a baroclinic zone, the flow can't be at tremendous angles to this through the thermal wind because it's that baroclinic gradient through the troposphere that's driving the vertical shear. So they're not unrelated. It has to be somewhat parallel. So you know what the biggest discriminator between convective mode is? Honestly, it's boundary type. It's not even the orientation. It's dry line versus cold front. If you know it's a dry line, your chances of discrete are much better than almost every cold front.
And a quick follow-up question. Which scenario, the cold front or the dry line, would you expect the model to do better?
Cold front.
So that poses because we kind of want to know discrete supercell favoring.
Okay, so yeah, so you're more likely to see a convective signal even in convection allowing models along a cold front than you are on a dry line. So in this case, the shear vector and the flow and the storm motion all are more parallel to the boundary. The storm motion, what's the component of the storm motion compared across the boundary compared to the movement of the boundary? Which one is the cold front moving as fast or faster than the storms? Or are they outrunning it? I don't have it drawn on here, but you can eyeball it. The storms can't get out of the zone of ascent on the front. And also another interesting thing about the front, how do fronts like this typically slope with height? rearward. So if you think of frontogenetic circulation along the boundary, the ascent slopes up and over the surface boundary. So a lot of times the storms will end up relative to the surface, they look like they're elevated. So anyway, last thing, I promise, QLCS tornadoes, we didn't talk about forecasting them at all. And I think it's fitting for when I'm tired and I don't care as much because that reflects reality. I'm just being honest. We're amongst friends here. You often see these in supercell-like environments. So the cool season southeast almost always has a supercell wind profile. But what it doesn't have is Great Plains buoyancy, and it may not have the Great Plains dry line initiating factors. So who's heard of the 3 ingredients method? So a few of you. Okay, all we're talking about here, and this is what forecast offices, they'll throw it around. It's been floating around for about a decade now. You identify the gust front on radar. Usually there's a velocity gradient and you can see the fine line, and you want to see the reflectivity close, all of this stuff co-located. And then you're looking for what they call balance. This is sort of gets all the way back to the Klemp, Wilhelmsen, cold pool shear balance idea that you're keeping the low level updrafts are vertically aligned over the wind shift. They don't slope back over the cool air strongly. They're right there in the vertical. And then you're looking for, and the way you anticipate that is you have line normal shear from the cool side to the warm side. Does anyone know what kind of frontal flow that would be called from the cool side to the warm side like that, or a shear? The opposite is anafrontal. So what is that? Catafrontal. So you're looking for catafrontal type shear profile, and you get mesovortex formation along and generally left of these balanced segments of the QLCS. And from my personal experience, there's a whole bunch of complicating factors. There are some really classic QLCS cases, and there's other ones that look like they are everywhere from the smallest of purest squall line mesovortex all the way to the clearest supercell line that you could imagine. Everything in between shows up. Okay, here's one. This is the El Reno tornadoes. Anyone remember that from 2019? There were actually fatalities. It was rated EF3. It was short track, but it killed people. Okay, so this is a typical scenario. You can see this is sort of this Boeing segment has come in out of the west-southwest, and this is just west, we're right over here. So it's just to the west-northwest of here. Here's one mesovortex reflected in the precipitation. You see a little velocity couplet with it. You also notice there's a couple of fine lines. There's one here. Note that the gust front is very close to the leading edge of the reflectivity and the wind shift in this segment, but how would you characterize it down here? Is the outflow ahead of the main precip and implied low level updrafts or not? Yeah, so that's what we call the unbound. This is the anafrontal part. You're looking for this, and it's usually the more north-south segments. So you get mesovortex. What is this fine line? It's outflow from other storms and the Boeing segments intersecting it. That's actually a really favorable pattern for these kind of things on the immediate cool side. The El Reno tornado, if you look at where the cursor is, or the center point, that's actually on the cool side of this. It's up in the cool air behind the very slowly south sagging outflow. And you end up, this is a very common location for mesovortex formation. It's just to the cool side. There's a lot of vorticity in the horizontal being generated through here, because again, it's a baroclinic zone. And echo tops and all this, these are not supercell type storms. They're just, so the swirlies tend to be where you get the north-south segments. And especially if you have other, would the updraft be stronger where the gust front the merger is, or weaker? Stronger. You've got more mass convergence in the low levels. So it's a stronger forced updraft along and just north of that. Even though it's in the cool air, it's actually a stronger updraft. Okay. You can get all sorts of goofball things in between. I don't know if anyone remembers this one from December of, was it last year? I think it was like 11 months ago, just down a little bit to the south. This is like at sunrise or just before. There's a tornado down because Norman's right up here, so it isn't that far away. And you notice here from the reflectivity, this is more of a linear structure, but where is the wind shift compared to like this stuff? Normally you think, oh, well, the gust front's way out here. No, look at it. This little vortex signature is back here. Now, this was one that had some supercell structure earlier and kind of a hybrid case. But the point is, we're looking at where these wind shifts. So in this case, there's not a classic fine line structure. And you can't even tell from the reflectivity, but if you look at the velocity, the wind shift runs through there. So you're looking for the updrafts co-located with that wind shift, and especially the more north-south cases, because most of the time, which way are the shear vectors oriented? From west to east, loosely. So more north-south segments are more common for this. And this ended up it's actually producing a tornado because there's a CC men and lofted debris, something got flung up there with oddball orientations. And you can see down south, there's even some cellular structure in the deeper updrafts. But point is, there's a lot of different flavors of this. You're looking for these things. Now, the way the Weather Service does it, and I'd encourage anybody who wants to look into this problem, we can do a hell of a lot better than shear vectors cross the gust front, tornado one. That's like the 1992 or 93. We put in the 88D, every supercell is going to produce tornadoes. No, it's not how it works. Okay, the one final thing I figure, since we got a bunch of SPCers came in this evening, I just kind of relate some of all these concepts to the way we try to forecast it and what's realistic to expect from us. Land spouts, QLCS tornadoes, and supercells. Typical outlooks for the land spout type things, you're lucky to get tornado probabilities, and these are going to be mostly day one as we get close to it. The QLCS stuff, typically you won't see higher than an enhanced for that kind of thing. That would be the more typical high shear, low cape, or modest shear, moderate cape, warm season cases. Supercells the entire spectrum. I mean, we haven't done a whole lot of 60 sig tornado outlooks. We could have, but it's just people shy away from the top of the scale. So important thing here is just to remember, eventually you have to put it all together in a coherent picture. I tried to throw in as much ADH stuff so that you can focus on it, but you're looking for the environments, you're looking for the initiation of the right kind of storms. And you can see in this was the May 24th, 2011 tornado outbreak that was almost very interesting right here at the building. So anyway, keep all this stuff in mind. And, if you're worried that, well, everybody already knows anything, what am I going to do? Keep in mind, this work's been going on for decades and we still don't have answers to important questions. And it will keep going for decades. So there's a lot of room for any one of you to improve on any of this stuff. So that's all I have. I really appreciate y'all staying late. And the 30 minutes is exactly what they set me behind. So I feel good that I did it in an hour. So again, thanks a lot. I know this is all voluntary. It's appreciated on our end. So hope you got something out of it. And if you have any questions, want to bug me, a couple of them can confirm. I will answer emails. So
Yes.
maybe.